Yes. Make sure I have 5 minutes.
Yep. Yeah. 2 minutes to go. 1. Okay, so hello everybody. Welcome to the second day of the workshop. Let me introduce myself for people who don't know me. I'm Cristian Teodorescu. I'm the leader of the group of surfaces and interfaces here in the Institute. And I'm proud to be the chairman of this session. I'm inviting now Paolo Fornaciero, who is a full professor at the University of Trieste, Department of Inorganic Chemistry. He's also head of department. And, sorry, deputy head, okay. So, he's the second head, okay. So, he's the neck. Yeah, so enjoy his talk.
Thank you very much. First of all, let me thank for the kind invitation. It's really a pleasure and an honor to be here in front of such good colleagues, friends, and new friends, I hope. Having the opportunity to share with you what was my personal journey in the design of heterogeneous catalyst for sustainable chemical processes. So, I'll start from a brief introduction which relates to the field where I am applied the catalyst we are developing, or we have been developing in the last decades. So everyone knows about the problem of pollution related to the use of fossil fuel, the global warming, and the changes in the weather we have today. I would like to mention that in Italy we had right now serious problems caused by terrible weather events, and many people died and have facing serious problems. So I think catalysis can do and is doing a lot to at least try to reduce those negative effects. And just to comment, this is not a today issue only, but the first legislation I was able to find in the literature dates back more than 700 years ago. And you can see here how serious was this legislation with torture. Even people were killed using stick coal when the parliament in London was working. So King Edward I was really a serious guy in this respect. Today's legislation, I think, is less severe. The second aspect I want to underline in this short introduction is that we have one planet, we have limited resources. This is something we start learning, probably do not have always in mind, but for instance, Easter Island had problem with trees. We know that the shortage of guano after its discovery and its importance as natural fertilizer. We are aware about the end of the cheap oil, so the energy we have to put to extract more deep and deep oil. But what I want to emphasize is something is missing. Well, there was a periodic table showing the different abundance of the elements which are present in the earth, and so how many of those elements are getting critical due to the use in some technologies. And related to this aspect is the energy we are putting to extract these elements. So we're talking about strategic elements. More and more attention is dedicated to these aspects, especially because many of the elements we are using, even in catalysis and technologies, comes from China, India, Vietnam, and in some cases Brazil. So there is a urgent need to think about how to design material as well as catalyst, and this will be the topic of my talk. The good aspect is that in Europe we discovered recently good reservoir of these rare elements in northern Sweden. Still, we have to face many years before production will supply these elements in Europe. And so there is great attention for even something we may today think is just a dream, like mining asteroids, but people are putting money in that direction, so we have to keep an eye on. So let's start on this journey, personal journey from my early career when I was a child, a PhD, and at that moment we were interested in car converters, which today is something very common. And the problem at that time was temperature and the presence of grams of noble metals, and in particular rhodium, 1 gram of rhodium, which is one of the most expensive elements used in car converters, and definitely much more expensive than gold. You can see, of course, with time you have this normal increase in cost. I would like also to emphasize that we have strong fluctuation in this cost of precious metal. In the case of rhodium today, the price is nearly half of what it was a couple of months ago. And you see 2 to 3 years ago was much, much higher. But it's not just a question of cost of these elements to make catalyst, it's also the abundance. If you look at the supply for rhodium, it's remaining more or less constant, and with the amount of rhodium you get per year, you could, let's say, prepare 20 millions of car converters, but the number of cars that were produced a couple of years ago today is a bit different. So they are slightly lower, is much, much higher. Of course, with 1 gram, the technology available 20 years ago. But having in mind that we were working on increasing the metal support interactions to stabilize the precious metal, to reduce their content, and that was important because typically we use much more precious metal than needed to cope with the usual deactivation you have with time. And so by designing a series zirconia mixed solution, we were able to reduce the amount of precious metal, in particular rhodium, to very low level. And that was also the beginning of palladium-only technology. The second step, a very important step I want to highlight in my career, that is in the direction of removing or reducing the content of noble metal or metals in the catalysis, was the investigation of well-defined Syria crystals, highlighting the formation of oxygen vacancy. That's much more complex. You have vacancy in the surface, in the bulk, single, double, surface, subsurface. And those vacancies started to be deeply investigated in those period and opened the possibility to understand the stabilization of first cluster nanoparticles as well as single atom catalysts. So very important also as co-catalyst. The further step in our research was the discovery that in some cases, some reaction like CO to CO2 oxidation perform on supported, well-defined catalyst. Not all the metal atoms has the same reactivity, but some, and in particular those at the interface and likely at the corners of this supported cluster, have a much higher reactivity. So the metal support interface is extremely important, and the message was to maximize that in order to reduce the content of these metals. So in this direction, we were much interested in see the activity of single atom catalysts, which is really a hot topic today. I would say there's a huge debate if those are single atoms, single sites, how to prove that really you have only single atom. And this is the first example in our joint work with Rades Boril in Ostrava and Olomouc, and I want to emphasize that we just gained a new European project on that. This was on copper. We have been working on many metals, different metals from gold, iridium, for different application, and I would say we have published not much because it's really challenging to prove that you have only single atom catalysis. And in the same period, with this idea to reduce the amount of precious, costly metal, we were interested in trying to investigate, let's say, functionalized carbon-based material as metal-free. Other very debate question is really metal-free, but metal-free material for different sustainable application. We focused the attention on the electrochemical synthesis of hydrogen peroxide, and this was very much interesting for us, and we managed in collaboration with CNR in Florence with Francesco Vizza to arrive even to a demonstrator producing quite decent amount of hydrogen peroxide with this type of material and very good conditions. As well as we investigate in carbon-based material for water splitting or for photoreforming. So today our interest is in a plethora of different reaction, quite relevant from an environmental point of view, like CO2 electrochemical reduction to formates, the electrochemical synthesis of hydrogen peroxide, photocatalysis for organic synthesis, hydrogen production, water splitting, and photoreforming. And let me try to show you something more in detail. So I mentioned how important is reducing the metal. The nanotechnological approach allow you to get a high surface area of the nanocrystals and to increase the reactivity. However, when you form this well-defined catalyst, the problem is, are those stable under real reaction conditions? And you have lots of processes that lead to deactivation, like leaching, carbon deposits, poisoning, and definitely sintering is a serious problem occurring with different processes, also ripening and migration, coalescence. So you make this nice nanostructure, and then with time you lose the properties. So we were focused on making core shell type material in which we first prepare protected nanoparticles and then we surround them with a protective layer of a porous scaffold that allows reagent and products to diffuse to and from the active surface. So this is a general scheme that we have applied for over a decade, and for instance, the case of platinum silica using hydrolysis of TIOS, ruthenium on zirconia, embedded into zirconia by co-precipitation method to decompose ammonia, important reaction, or for making photocatalysts, like in the case of copper, titania, by microemulsion, as well as with the self-assembly method starting from metal nanoparticles protected by carboxylic thiols and the coordination of metal alkoxide. This is quite general routes, not only for palladium, but platinum. We have used Syria, titania, different application. And that was good results in methane catalytic oxidation. Definitely these are very attractive synthetic routes for science, but not so appealing for companies. So we move on from those syntheses towards the atomic layer deposition, which is very useful technique to control the formation of layer over a preformed catalyst with nanoparticles. And it's quite flexible and appealing also for company. Here have some disadvantages, but you can work even with a right quantity of these materials. So we demonstrated with at use of atomic layer deposition that you can cover standard, let's say standard catalyst for like this palladium-based material with thin layers, and you can control how many layers of your oxide you're putting, and reducing definitely the sintering problem, the deactivation, which allow you to use much less precious metal. In this case was palladium, but I want to highlight one other important aspect. If you're using a reducible oxide, the metals that are entrapped in these layers can undergo exsolution process, which leads to this metal to come up to the surface and back reversibly, depending on the redox thermal treatment you apply. So in some way, these catalysts are quite smart. They can also self-regenerate. And this is okay, it's something strange, probably. It disappears completely the other parts of the slides. So in this other in this other case, we proved that the use atomic layer deposition to protect this catalyst is more general, and it works with in this case of this platinum-based material. And the beauty is that you can form this nice triangular shape of cluster for platinum atoms that goes up and down from this layer and are very, very stable under redox cycling. So what we're doing today is try to apply these strategies of protected nanoparticles for important industrial reaction, like propene dehydrogenation. You can see the number here, which tell you how important is this process. And the state-of-the-art catalyst is platinum tin, which, however, has the problem of deactivation due to both coking and sintering, and I would say more sintering because the amount of coke which is formed depends on the dimension of your platinum tin particles. So increasingly the sintering, then you increase the coking. And the industrial process, which works, requires very often the regeneration, very frequent regeneration step. Many had this idea to protect the platinum tin catalyst embedded into zeolite, and this works because there is an extension from the stability from hours to days, but still this requires regeneration step. So this is very, very, very long joint collaboration for many years. The work is still under consideration. You see many institutions, Dalian Chemical Physics Institute, University of Fuzhou, KAUST, and our university. And here we use something known, platinum tin. We use a zeolite, but we were deeply investigating the anisotropy, obtaining for very long crystals astonishing long stability over 6 months of operation. So it's really unimpressive results from my point of view. I will mention that in this trend we are working a lot on single atom catalyst, where the characterization is our nightmare. This is the first example we publish, in which we use channel graphene to coordinate copper. The beauty of this work is that you have single atom, but you have copper 1 and copper 2, different oxidation state, as proved by EPR, and they are talking each other. Very important synergistic effect between the two different oxidation state. If you reduce the amount of copper you have, so you have more isolated sites, the organic reaction that we were performing are not so so good. So the yields are much lower, significantly lower. In some cases, they do not occur. So I think it's the first example of synergic effect between two different single atom catalysts. And the last part is to try to remove metals completely. And we focus the attention on graphitic carbon nitride, very popular material. I'll try to show you the reason. Definitely, if you think about photocatalysis, very popular topic, you have so many papers, and you can see titania here is a benchmark system, highly investigated. But you can see here how quickly is becoming relevant this type of material. Why? Because it's stable, it's made by carbon and nitrogen, so abundant elements. It's easy to be made in different ways. You can modify this material with many treatments, as I'll try to show you later on. So it has a band gap in the visible region, so it's useful, promising material. So what we have done is a very simple synthesis reported in the literature, starting from melamine treatment in air. You get this yellow powder that we have treated in different ways in our gas, high temperature, to make a material which is amorphous according to XRD and the TM and characterization. We apply a reductive or an oxidation treatment to get an oxidized material and a reduced material. And we have used this for making perfluoroalkylation reaction, which are important to make materials like liquid crystal precursor, molecules important in agrochemistry, in pharmaceutical chemistry. So this is just the first reaction test that we have used. And you can see that these different materials treated differently behave in a different way. So the amorphous material is the most active, the reduced one, lower activity, and the well investigated by most of the research of the graphitic carbon nitride is active but poor activity. So we spend a lot of time to understand reaction mechanism, what is the reason for that in characterizing this type of material. Is an ongoing work despite many publications. We're still at the beginning of a very promising story. So we use NMR in collaboration with Carmelo and Agostino in Manchester, and in particular the interaction of this perfluoroalkyl iodine, which is a probe molecule for our reaction, and the relaxation time T1, T2 is an indication of how these molecules interact with the different materials, and you can see that the relaxation times match well the order of reactivity. So this is a strong indication that in the first step, what is extremely important is the coordination of the perfluoroalkyl iodine to the surface. Then we have deeply investigated the radical nature of this type of reaction by EPR, and the situation is very much complex because even in the absence of all the reagents under illumination, graphite carbonitride has different radical species formation. I can anticipate that the amorphous material has much more of this radical species, surface radical species, different radical species, so it's quite complex. And so this mechanism that we started to propose is still under debate, but what is the message is that this material is becoming so important, so flexible, and you can modulate it nicely. And changing the reaction test, the order of reactivity is different from the different material. They are extremely reproducible results. So you can see the plethora of reaction you can perform, even using sunlight outside our department. Yields are extremely good as well as under well-controlled conditions. So I want also to mention something different, something funny we're looking at. So those are very well-known installation that you can see in California and different places. So you can concentrate the light in a tower, reaching very high temperature, but the problem is that you need huge space and you do need costly mirrors. So it is something you have already in reality, but it's just a question of cost and space. So what can we do? And we're trying to open a new type of chemistry. So we're looking at plasmonic materials. So plasmonic materials can be gold, can be silver. Those are expensive. We don't have much availability of those elements. So keeping in mind that we were focusing on titanium nitride. Titanium nitride has this metallic plasmonic character. Here we add a step further, making nanotubes, titanium nanotubes treated with ammonia, high temperature, you get this, what we call nanocavities. And if you're familiar with titanium nanotubes, you can play all the parameters, dimension, and therefore you get these different cavities of titanium nitride. And there, with just the power of, let's say, 10 suns, you get the temperature you need for catalysis, thermal catalysis, and then you can use it, this nanocavity as nanoreactor. There are problems, stability in oxygen, so you have to protect, then you can make all the catalysts you want, single atom catalysts, for instance. And I want to highlight this Joule paper, which indicates how important it is to correctly measure the temperature in this catalyst. And last two slides are just a collaboration with a friend in China, from Dalian Institute of Chemical Physics, related to biomass to liquid hydrogen carriers. Is a photocatalytic process that we have just published on this project, with the bilateral project supported by our government and Chinese government, which use doped ceria with tantalum, which is able to absorb visible light, and therefore starting from hydrolysis of biomasses, we got sugars. We had to remove lignin, but then using these sugars, you can have flow type photoreactor with our catalyst, and by tuning, we need some oxygen because the process is radical, some oxygen or air, works even with air, and you have to set the right temperature. You see here we have in this demonstrator Fresnel lens. If you're able to, let's say, work 120 degrees Celsius, which is not high temperature, you have a very good conversion, decent yields in formic acid or formaldehyde, starting from different biomasses. So this is extremely promising also in terms of valorization of biomasses to liquid hydrogen carriers that can be easily then decomposed back to hydrogen. So with this, I hope to have been able to show you that we have done in Trieste a journey starting from heavily loaded metal catalyst to single atom, in some cases metal-free catalysis, always keeping in mind sustainability. The design of the catalyst, in our opinion, must look at the availability of these metals, and so I think this is the trend. The future is bright, but there's much more to do. I want to thank a member of my group, particularly Professor Tiziano Montini, Professor Michele Melchionna, many young guys. Special thanks to Matteo Monai and Matteo Caniello now in Utrecht and in Stanford, who contributed to the first part of the talk, some of the early study I mentioned. Financial support, I'm lucky. It's a rare case that I can show significant number of European projects. Was just last few years that we succeeded at, as well an Italian project, which is maybe even more challenging if you don't know the Italian, I would say mafia, but no, maybe not. My Italian way to evaluate project. So I'm even more proud to have this. Is ridiculous in terms of the money. But in terms of prestigious is amazing. Many collaboration, let me say, thanks to Maurizio Prati, University of Trieste, Ray Guarti, and Chris Murray, UPenn, good friends, many other, and thank you very much for your kind attention.
So thank you very much. We have 5 minutes for a few questions.
Thank you for the very, very interesting talk. So I'm very interested in the propane to propylene and dehydrogenation reaction. So you used the platinum with tin catalyst. So may I ask what's the function for the tin inside the catalysis, and also like what's the selectivity towards like propylene?
Well, this is the standard catalyst which is used in the literature and the plants. It is nothing new. So it's interesting. There is lots of theoretical investigation on the role, and it seems that you may have dimers of platinum tins. The importance is of the tin is in both the stabilization and so in making more stable the platinum as well as the selectivity. But my point is, this is not new. If you look at the literature, you find plenty of those examples, as well as platinum tin in zeolite. That has been investigated and shown that you can improve, depending on the condition you're using, the stability from hours, where you see strong deactivation, to weeks. But that was stopped. So now this paper is under evaluation, good journal since long time. And we're fighting because they wanted to know exactly what you're asking me, which is the active sites, and is there any specific reason? Because yes, we increase a little bit the stability, but we see moving this cluster, but not making nanoparticles. So the trick is really the very long crystal with very long channels. So the diffusion in some way of this isolated species occurs, but they do not merge. So the editor has to do operando exos. We had problems in that because many synchrotrons were shut down due to the cost of electricity.
Okay, thank you. Just one short question. If,
So, Professor Fornaseiro, please, you showed us very beautiful palladium nanoparticles triangle obtained by exsolution. Can you control the form and the dispersion of palladium nanoparticle obtained by exsolution, please?
Well, in theory, well, most of what we do could be said we designed, but it means we spend a lot of time trying to find the conditions. So yes, depending to obtain those particles, you have to apply oxidation reductive treatment. Which temperature, for how long? Yes, if you change those parameters, you get larger, even other different shapes. The rate you eat the material is also important. So the amount of hydrogen or oxygen you put. So yes, but we have not investigated how to optimize the process. But we notice differences in the shape and the dimension of those triangular features.
Yeah. Paolo, thank you very much for your talk. I'm just interested in single site atoms. Is for sure a very challenging question, but my curiosity is about the synthesis method. Which approach do you use in order to control the single site?
Well, in this case, I show you that we're using graphene. So the trick is to have functionality on the surface, and so we use fluorinated graphene, then we make chanographene in order to have, let's say, one single functionality on the surface. Because if you oxidize, for instance, graphene, you have different carboxylic, hydroxylic groups, and then you have different species on the surface. So really the trick is to have one type of coordination sites for your metal precursor. That's why we are not trying to use, for instance, Syria or titania, because then the question is you have a not well-defined support. You have many vacancies, different steps, and so you may also get single metals, atoms, but then the support has different roles, and so you have different catalytic sites. We use XPS and different techniques to prove that these functionalities are only those we wanted. And we can enter, is 100% chanographene, or you still have 1% of fluorine on the surface or other functionalities. Is oxidized? I would say, yes, you're right, is 99, and then, well, I anticipate question, single is difficult to be proved. But the beauty is that they perform very well. Question, can we really understand, characterize? It's much more. Yeah, it's a question. And I can tell you that we're working on iridium. It was a nightmare. We were not able to really prove iridium for electrochemical application. Very important to reduce the amount of iridium. Very difficult to prove a single atom. We worked for years on gold. And I always found some small nanoparticles. And so it's...
Okay, thank you. I think you can continue this interesting discussion during the coffee break. So thank again the speaker. And I'm inviting here the next speaker, who will be, so sorry for your name is, I will spell it in English, Jeroen van Boekhoven. Is that okay? It's more or less okay. He's professor at the Technical University of Zurich in Switzerland.
Good. Thank you for having me here. It's a great pleasure. I very much enjoy the discussions after the talk, so make sure you give a 25-minute warning that I'm done at 30 minutes. And many speakers already alluded to structures of catalysts. In the theoretical talk yesterday, it was very beautifully said that operando conditions are important because the structure of a catalyst is a function of its conditions. And exactly that makes it so difficult to characterize a catalyst. What I'll do in my talk, I go back to what I typically do in my lecture. Yeah, I'll show you adsorption isotherms and what's the consequence of that for the structure of a catalyst. And from this, I think you should be able to deduce yourself that it's extremely difficult to identify what the actual active phase of a catalyst is. It only makes sense to characterize your catalyst if you have a decent, or I would say a good idea about the mechanism. Very simple scheme. In catalysis, in heterogeneous catalysis, this is a surface phenomenon. Yeah? So first what needs to happen is you need to adsorb your reactants. Next there is a surface reaction, and then the products need to desorb. It was already said, if the adsorption is too weak, you don't do surface reactions. If the adsorption is too strong, you never desorb, so there is no catalytic reaction. So you have to be somewhere in between, in the bonding strength. Rate limiting steps. If adsorption is the rate limiting step, you don't have to look at the surface reaction. Yeah, you want to understand adsorption. If the rate limiting step is the surface reaction, one of the surface reactions, that's where you're going to have to go. So you really have to know where am I in my scheme. And of course, there's many steps in a catalytic process. So which of the steps are you actually characterizing? Second, a catalyst is very often not a single unit. When we talk about a single atom catalyst. Be careful what you're saying. This is a monodispersed atom on a support. This atom feels its surrounding, and its performance is determined by its surrounding. So the catalyst itself is not a single atom. It's an ensemble of atoms, and atoms far away may actually contribute to what this atom is actually doing. So I'll talk about the pressure gap. Low pressure, high pressure. Why is it important to think about high pressure? Because commercial processes are operated at very high pressure. If you characterize your catalyst at low pressure, there is no guarantee that what you have characterized is relevant for what actually happens in an industrial process. And of course, if you want to understand the functioning of a catalyst, we need to start simple, understand simple processes, simple materials, modify the materials, make them more complex, but make them look like an actual reactor, go to conditions where you are under actual reaction conditions which are relevant. And I'll show you how enormous important taking care of the pressure gaps. The pressure gap is a materials gap, and I hope you convince you of that. I'll look at copper zinc oxide alumina archetype catalyst. Multi-component, this is a catalyst for methanol synthesis, commercially used since decades. It's active for water gas shift. And there's many discussions about structures of active sites, active phases, and over the years, there's been very different schools in identifying or claiming what are structures of active phases, and I will give you my view on this material at the end of the talk. Typical methanol synthesis, all important, probably more important than ever. If you want to synthesize methanol from carbon dioxide, you have methanol. Out of methanol you can make olefins. Out of olefins you can make chemicals, fuels, and so that would be a nice viable route. But typically this is done medium high temperature, high pressure. 50 bar. Ammonia synthesis, high temperature, medium high pressure. Fischer-Tropsch, done under pressure. Water gas shift, depending what kind of water gas shift you do, but this is a pressurized system as well. So if you want to understand how these catalysts function in an actual reactor, you have to start characterizing these materials under those pressures, which of course is difficult. It's certainly not a starting point where you go. I already mentioned you start simple with simple systems. There's a reason why single crystals have been studied so much. A relatively simple system, you know where all atoms are, so you have good control of what you do with the surface. You can learn a lot. The language that we use in catalysis comes from that kind of research. But slowly but certainly we need to go to realistic systems. Then in situ operando, already mentioned. The structure of a catalyst is a function of its condition. Very simple, in ultra-high vacuum you may have beautiful surfaces. But if you pressurize your system, the surface may be different. Or maybe I should say most likely is different. But if this is true, if the catalyst structure is a function of its condition, then the premise of course is that only the structure that you measure under pressurized conditions may be relevant for catalysis, for understanding structures of catalysis. Then it's keep in mind, if you have a catalytic reactor, what you put in is reactants, what come out is products. So the initial phase of the catalyst, the initial catalyst that sees the reactants, does not see the same gas composition as the middle of the reactor or the end of the reactor, because you have conversion. There's intermediate formed, there's products formed, and they actually may change the structure of your catalyst. So if you characterize your catalyst, it's extremely important to exactly know the gas composition at the point where you measure, which is not straightforward and easy. So when we looked at this, we were interested in situ electron microscopy for methanol synthesis. Then, of course, I said, we want to do this at high pressure. Then they said, well, 1 bar is the limit. So then the first question came up, how relevant is looking at 1 bar? Then we started looking in the literature. So where in the literature are people bridging the gap from extremely low pressure to very high pressure? Many people talk about the pressure gap, but very few are actually bridging this in a single study on the same material. So that's where we started. We said, we're going to characterize materials, in this case the copper zinc oxide, across the pressure gap and just look at the structure. That's where we started, and of course it was to identify the relevance of doing in situ electron microscopy at 1 bar. So you have to understand what the surface of a catalyst looks like. Now, these are very simple considerations. These are Langmuir isotherms. So as function of pressure, here we look to the coverage at different temperatures. And this is typically a surface coverage of hydrogen on platinum. We assume 70 kilojoule per mole absorption energy, which is reasonable. But what you can clearly see, if you look at 100 degrees already at relatively low pressure, the surface is occupied by hydrogen. But if you increase the temperature, the coverage goes way down. If you measure in ultra-high vacuum, there is going to be very little at the surface. If you measure at high pressure, it depends on the temperature. So here is the similar figure, but now as function of temperature. So the coverage is a function of temperature as function of the pressure. If you work at 10 to the minus 5 millibar, which is low pressure, you can see at 0 degrees, not much at the surface. My surface is empty. If you increase the pressure, where the temperature where you still have things at the surface is increasing. Of course, you can simulate different heats of adsorption. If you have 120 kilojoule per mole heat of absorption. This means this is a very strong bond. Most likely this is a poisoning bond. That is, so at very low pressures you have full coverage, but really as function of the bond strength, the coverage goes down. All common sense logic assumptions. Same thing if you look at the temperature, the coverage function of temperature. The stronger the bond is, the more coverage you have at higher temperatures. So why is this important? If you have nothing at the surface, if there's no oxygen at the surface, you'll never oxidize your surface. If you have a surface cover, a certain coverage of oxygen at your surface will reconstruct. Eventually it will oxidize. Theoretical predictions of the surface of platinum 111 as function of the oxygen pressure and the CO pressure. So depending on those pressures, you're going to have actually different surfaces. The surface will reconstruct into different surfaces as function of pressure. And what is important to realize now, if you measure the structure under these pressure conditions and temperature, it's not possible to predict what the structure in a different location is going to be. You're going to have to actually determine that. So what's the consequence of this relatively simple consideration? You cannot predict outside your experimental scheme. If you measure under certain conditions, be very careful to extrapolate your conclusion into different regimes. Pressure gap is a materials gap. There is different possible reaction mechanisms of species. And this is a very simple consideration again. So this is the relative rate versus a function of pressure, assuming there is competing reaction mechanisms. A reaction mechanism where you have half order in reactant, order 1 and order 2. Then even as function of pressure, you can see that the rate that wins out is different. So actually you may go to different rate limiting steps as function of pressure. So if you have measured your system here, the most prevalent mechanism will be the order 0.5, and if you go beyond the point here, it's going to be the order 2. So mechanisms is a function of pressure. Good, so now we apply this basic understandings to methanol synthesis. Methanol synthesis from carbon dioxide. If you have carbon dioxide, instead of putting it in the air, if you can make methanol out of it, again, methanol is a very beautiful resource for many chemicals and fuels. So there is environmental concern that may help us alleviate this. It makes chemicals and fuels from carbon dioxide. And of course, there is a huge scientific debate about the structure of this catalyst. So the big question really is, what's the role of each of the components in this multi-component catalyst? Copper on zinc oxide on alumina. It's a very famous system. For decades it's been used. For decades it's debated what the structures of the active phases is in this system. It's a dirty system. So to say, there is nano-sized copper particles attached to nano-sized zinc oxide separated by alumina patches. And there's a very specific ratio of these elements that gives you the best system. If you go in the literature, there is a plethora of explanations of why this system is actually active. There is claims that the zinc oxide is there to separate copper particles, preventing them from becoming bigger particles. There is claims that it's the zinc oxygen copper interface. There is copper zinc alloy. Claims that it's active. And there is actually the classical encapsulation of copper by zinc oxide, as well as alloyed particles encapsulated by zinc oxide. So there really is a whole plethora of arguments that suggest to know what the active phase is. Copper oxide has been claimed to be active. Zinc oxide has been claimed to participate, or has been claimed to be inert. So there's a whole slew of, and you can add your favorite paper here, right? And I add ours down here, which is just another thought of the same system. And so we systematically looked at the structure of this catalyst as function of pressure. So the most simple thing that we could imagine was doing a temperature programmed reduction. We did that as function of the hydrogen pressure. Low pressure, sub-millibar range, high pressure above 15 bar. Yeah, and the beauty of X-ray absorption is that we can actually do this. We can load our catalyst in an actual reactor. We can shine right through the reactor. So in an actual reactor, you can look at the structure of your catalyst. So basically what we did a temperature programmed reduction. Yeah, so as function of time, we increase the temperature. Yeah, and then we looked at different hydrogen pressures. And we simply looked at the structure of copper and the structure of zinc oxide as function of temperature. So the figures that we get on the left is the copper KH and on the right is the zinc KH. Here's the measurement of the temperature. Yeah, and that you can see you start with copper 2. Yeah, and then at a certain temperature you're going to see that the spectra change. So it's then copper is going to reduce. You're going to make first copper 1 and eventually you're going to make copper 0. And actually what you see the moment that you start forming copper 0, that's the moment that the zinc edge is also going to change. Yeah, so really they communicate to each other. Copper reduces first, and then some of the zinc oxide phases are partially reduced. And the beauty of this method is that you have a quantitative view on your species that you have in your sample. And you're very sensitive. Better than 1% of the atoms we really are measuring. And of course, this we can quantify. Yeah, so this is the different pressure spectra, and then the color represent the same temperature of the measurement. And you can see from the color coding that the reduction profile is very different, both for copper and for the zinc. Now we can quantify the species that we have. For copper it's very simple. We have 1 millibar of hydrogen. At 275 it starts reducing. We make an intermediate, which is copper 1. This intermediate goes to copper 0. So we go from copper 2 to copper 1 to copper 0. Classical reduction of copper oxide. Then at increasing pressures of hydrogen, same thing happens, except it happens at lower temperature. And then at certain pressures of hydrogen, we hardly see the copper 1 intermediate. And then there is no dependence on pressure anymore. So then copper 2 directly goes to copper 0. So the copper 1 is too short-lived to see we interpret that. Of course, life is much more complex than that. If you look to the zinc, zinc at 1 millibar looks very straightforward. We have your starting zinc, which actually is a hydroxide, this is some kind of carbonated species, and at a certain temperature, which is exactly the temperature where copper reduces, we make zinc oxide, we reduce the precursor phase. This happens at lower temperatures, at slightly higher pressures of hydrogen. But then if we start working at 100 millibar above 300 degrees, we start seeing the partial reduction of zinc 2. So at function of pressure, zinc is going to change its structure. Of course, the question is, what is the zinc phase that we are going to actually form? We interpret this based on spectral analysis that zinc oxide goes to defective, partially reduced zinc oxide. Only at higher pressures, we start seeing a zinc copper feature in the X-house. So there we're going to see alloy formation. So what happens first, zinc oxide reduction, and then we have at 1 bar, we start seeing copper zinc alloy formation at temperatures above 300 degrees. So the reduction profile and active speciation are really very strongly structure dependent. We can determine the reduction rate of copper reduction. Every decade of pressure, there is about a 40 degrees difference in reduction temperature. You can do some engineering with that, but really there's a very strong pressure dependent of the reduction of copper oxide. And the zinc oxide is actually answering what happens on the copper. You need to have the copper to make the changes on the zinc. And as soon as copper is reduced, zinc starts reducing. This is all trivial. If you give an oxide example to somebody Yeah, and you give him 10 to the minus 4 millibar of hydrogen, and he or she comes back and says it doesn't reduce. Well, what do? Well, crank up the pressure. That's exactly what this is. Pressure-dependent structure of your materials. But the consequence of this, if you look to this, this is pressure dependence versus temperature dependence. And then the color coding shows the different structures that you will have. So really depending on where you are, and this is quite subtle, if you have differences in temperature or differences in pressure, you have a completely different structure of this material. So this directly shows it's going to be extremely difficult to make a model system at all, because the structure will depend very subtly on your conditions. And then of course the next question comes, well, which of these structures is actually relevant for catalysis? If we make a model system, which would be copper on zinc oxide, where we prevent alloy formation, if you change your conditions, alloy formation may occur. So again, extrapolating from outside your experimental conditions is extremely difficult to do. It's not difficult to do. You should do this with extreme care, if at all. So really the pressure gap is a materials gap. Different pressures, different temperatures gives you different materials. It's very sensitive to the hydrogen pressure copper reduction. Copper 1 oxide is a short-lived intermediate. We do not see copper zinc alloy formation at pressures below 100 millibar, and there is reduced form of zinc oxide prior to brass formation. So now we try to identify under actual catalytic conditions what are the phases that may be relevant for catalysis for this reaction. The fact that this system is so chemically sensitive to the conditions, well, that is one of the reasons why this is a very good catalyst in the first place. Because it chemically responds to its environment. It's reactive. So what we try to do is try to use Sitka, isotope switching of one of the reactants, and then see what happens to those species at the surface and as the products, so you can identify what are reactive intermediates. And we combine this with the X-ray absorption. We did this all at elevated pressures of 10 to 15 bars. So Sitka, there's a rapid switch from unlabeled carbon dioxide to labeled carbon dioxide. And of course with infrared you can beautifully see on the surface if there's labeled species on the surface versus unlabeled and how fast they are exchanging. In a mass spec at the end of the reactor, you can actually see what comes out of the reactor. You can nicely correlate what's at the surface and what comes out of the reactor. So if you do that, and then here are the different spectra in the infrared. And what you see is the moment that you switch from carbon 12 to carbon 13, you see that the formate asymmetric switch is decreasing in carbon 12 and increasing in carbon 13. So the symmetric and the asymmetric formates are the species that actually exchange. Those are the reactive intermediate for methanol synthesis. We see CO formation quite rapidly, and slightly delayed is the methanol. Of course it needs to hydrogenate further, but the formate is the reactive intermediate under these conditions, which is 15 bar. Formates are primary products and undergo full conversion during the isotope switch. The question is, where is the formate? Is it on copper, is it on zinc oxide, or is it on alumina? Well, for X-ray absorption we can measure that. We can see what the structures is. So basically we did exactly the same experiment in the X-ray absorption. So where we go from a pre-reduced sample onto catalytic conditions at the same pressure and temperature. We look at the copper KH. After reduction we have reduced copper. After switch to reactive conditions we have reduced copper. Copper is not responding. You now look to the zinc KH, where we can have speciation. So we have partial most of it is still zinc oxide. Part of it is copper zinc alloy after reduction. And the moment that we switch to catalytic conditions, most of the brass is actually reduced back to zinc oxide, and there is a certain concentration of zinc formate coming up. So we spectroscopically measure that the formate is on the zinc. And if you switch back to hydrogen, the formate is reacting back again, brass is reforming, and the zinc oxide is the source of that. So really the zinc formate, the reactive intermediate. So what happens? If you have any copper zinc alloy, this to a large extent de-alloys under reactive conditions. Formate is the reactive intermediate, and the formate is associated with the zinc. Copper is a reduced species, a particle, and we think you need the copper to split the hydrogen. Good, my last slide. Conclusion, be very careful to extrapolate your results. On the left side, this is the proximity to industrial process. So if you start at ultra high vacuum, industrial process is very much high pressure. Of course, your conditions are going to be different. You're not going to have the same coverages on your surface. You're not going to have the same structures of your system. But of course, you can learn a lot about reactivity of those surfaces. If you increase pressure, for example, or you go to more relevant temperatures, or you go to more relevant flows, you are able to learn more about your system. But we made an arrow here, which is a dashed arrow. This is a step function what you can learn. And with that, I mean that you can learn something that you could not learn before. So more and more you go to actual catalytic reactors, where you have real particles. You're going to learn something more about the system. And of course, we need to make each of these steps and try to understand that. So everywhere we need to understand what the system does, and same thing for materials. If the proximity to the industrial catalyst, so if you define a model system, be sure that you are somewhere where you know where you are. If you're in a single crystal, you're not going to look at the metal support interface. There is no support. So you cannot make conclusions about it. And then you go more and more complex, and you make step functions in what you can learn. But I would argue that if you work in a regime here, do not extrapolate up there. Be very careful to do that. It's, good. Maxime, very brilliant postdoc. Arik, brilliant PhD student who went to the US now. Are thanked for most of the work that I show here. There's many more people involved. Mark Newton for X-ray absorption analysis. Vitaly Shushkevich, who designed and developed the high pressure Sitka. Dennis Palagin for the theory that we've been doing on this. And then Mark Wielinger, he's doing the in situ electron microscopy, who was the driving force in starting this in the first place. For Frank Roemeig for always doing our electron microscopy. And then of course Maarten Nachtegaal, Olga Savonova, who are the beamline scientists where we did most of the measurements that I show you. I thank the Swiss National Science Foundation, ETH and PSI for funding. And then of course the many beam times that we had at the many beam lines that we needed to do to get to this result. So I hope you have some questions. Thank you very much.
Thank you very much. And there are some questions.
So thank you very much for this very nice presentation. So I have up to 2 or 3 very short questions. So first, so with you copper and zinc oxide. So what is the optimized pressure? Can you increase again the pressure and to get effect the low temperature of reduction?
To answer that, I would go back to patent literature. If you read the patent literature in how they pre-treat their catalyst to do the pre-reduction, this is an extremely careful process. Relatively low pressure of hydrogen, increasing temperature, even decreasing hydrogen pressure before they increase the temperature further. Yeah, so this is an optimized, I would say that is an, well, in industry optimized procedure, and actually it's to prevent large structural changes in the catalyst. Yeah, so from that I learned that you do not need a high pressure hydrogen reduction to get your best catalyst. And actually you don't need to do a high pressure hydrogen pre-reduction to get your best system.
Yeah. Second question. Yeah. So what is about the porosity of support alumina?
Good question. Alumina, I should say, is the minor component in this material. So it's not really a supported system in the sense that you have a dominant alumina support where you have a low loaded copper and zinc. No, it is copper, zinc are the dominant elements in this system. Yeah, that is, there is patches of alumina left and right. Yeah, the role of alumina is, I mean, also from the literature, it's not really obvious. Yeah. Yeah, and it may not even be chemically inert. Yeah, that is.
And if so, in this case, so what is the porosity of a total porosity of your catalyst?
You mean the BT value?
Yeah.
It's tens of square meter per gram. Tens, 40, 50, I don't know exact number by heart.
Yeah, okay. So sometimes when we have the porosity inside, so in fact the pressure effect on the surface and on the pore is very, very different. Yeah. The atoms in the pore will feel differently compared to the atoms at the surface.
Sure. I sure that, but I mean the copper and zinc oxide are not within the pores of alumina. Yeah, there's not enough alumina to have this really is an exposed copper particles on zinc oxide particles with patches of alumina around. Alumina is really the minority phase in this system. That really makes the best catalyst. That's an optimized ratio, and I mean you can make this. You can put the copper in the zeolite, you can put the zinc in the zeolite, and then you make various kinds of copper zinc phases. And this is also a very active catalyst for this, but it doesn't perform as well as the commercial mixture.
So just the last comment, small comment, yeah.
So sorry, we already monopolized the discussion. So there are also some other colleagues that want to put a question.
Compliments, very convincing. Just a very short curiosity. You focus the attention on the pressure of hydrogen. Have you investigated the role of heating rate on the modification? Of course, it doesn't change the meaning, but I would expect if you change the heating rate to have different results.
Very good point. Yes, the heating rate is going to affect what you end up with in your structure. Well, this is something we haven't per se identified in detail. I mean, what we looked at was stopping the heating ramp at a certain temperature and then wait, and then you can see that the structure of the catalyst is still being modified. Yeah, but I mean, there are so many parameters here that we can, and of course, we only looked at CO2, which of course is not even the ideal concentration to look at, because any CO2 conversion you do, you're going to make CO. So the next steps, we're going to have to look at CO so there is much to be done. Yeah, thank you.
Okay, so thank you very much. I think there are a lot of things that can be discussed after the break. So the next speaker comes from New Haven, from Yale University. He's Eric Altman. He's the professor of chemical engineering. So please, Eric.
Okay, thank you very much for the opportunity to tell you about our work. So we were supposed to be here 2 years ago, but couldn't come because of the pandemic. So I'm excited to get the opportunity to finally come to Romania, and thank everyone for their hospitality. Okay, so an overview of the talk today. Do we have a pointer? It's over here. Great. Which one's the pointer? The top. Okay. Nope, that's not it. I have it upside down. There we go. Okay, great. Thank you. So overview of the talk today. So I'm going to be talking about high resolution AFM. So I'm going to describe how that works and how it doesn't work. We're going to talk about our extension to resolve the force fields in 3 dimensions and yields potential energy surfaces. That's this picture down here. We'll talk about the forces to move atoms and molecules, which will tell you about not only the interaction with the tip, but the interactions between molecules. That's this part over here. We'll apply that to benzene and phenyl radicals on copper 100. And then we're going to talk about imaging molecular structures with functionalized tips. And the application there is to this cobalt phthalocyanide CO2 reduction catalyst. Okay, so we want to image individual atoms with AFM. And so the usual way with AFM, you take the soft cantilever, you touch the surface just a little bit, and you measure the deflection. So if you do that, you'll have this large contact area, and you'll never be able to see that specific missing atom. So that won't work. Okay, so then you say to yourself, well, we know that in addition, I should stand over here. In addition to the repulsive interaction, which is this part of the curve, there's also an attractive interaction. So if I just do my measurement over here, I should be good. The problem with that is the force is steeper over here than is the cantilever spring constant. So what happens is if you try to go over here, you end up over here. And again, in this situation like that, so that won't work. Okay, so you come up with this idea that what you're going to do is oscillate this cantilever and just measure the amplitude of that oscillation, which will be affected by the proximity to the surface. The problem with that is this frequency at which you oscillate will also depend upon how close you are to the surface. And so if you just look at the amplitude, what will eventually happen is you'll also touch the surface, and that's tapping mode, so that also doesn't work. Okay, so the idea then is you try to always oscillate this at the resonant frequency. You measure this frequency. You try to keep the amplitude constant. And so you do all of these things, and that does work. So that's called frequency modulation AFM. And then you've probably seen this. Instead of using a soft cantilever, you take the tuning fork from a quartz watch, you glue a tip on. Now this is millimeters. And so this is so stiff that you don't do the jump to contact. However, this is so stiff that the signal at DC is immeasurably small. And so to get a signal, you oscillate this at a high frequency, then you get an AC current, and then you can measure it. So you're still doing this kind of thing. So here's what this scheme looks like. This is the frequency modulation AFM. So you have to you oscillate this piezo over here, which causes this to oscillate. Then you have to always try to oscillate this at the resonant frequency. So you have a feedback loop over here, which does that. So you have to tune that one. You have to keep it at constant amplitude. So you have another feedback loop to adjust. And then you have your typical SPM controller. So you need your student to tune 3 feedback loops. So this is very difficult. So what we came up with a few years ago was what we call tuned oscillator AFM. So now we don't have the jump to contact problem, so we don't worry about that. So we do amplitude modulation AFM. But if you do that at ultra high vacuum, this cantilever has such a sharp resonance that you're either oscillating or you're not oscillating. So what we do is put in this phase shifter over here. Right here we call the oscillation tuner, and that broadens that resonance. So now you can do amplitude modulation AFM in ultra high vacuum. So now Sienta Omicron has licensed this. They call it Q-Speed. We call it tuned oscillator AFM. Great, so that's how you get atomic resolution. And now we want to get quantitative information on how strongly the tip is interacting with the surface. So what you do is you typically measure force or amplitude as a function of distance, but to convert that to a quantitative force or energy, what you need to do is measure all the way back to where this goes to 0. So the way we've done this is you collect a series of images as you move further away from the surface, and then once you hit the point where there's no longer any resolution, you only need one curve, and then you meld all of these together, and you get a whole bunch of curves at every pixel in the image, and you can slice it and dice it, get any potential energy surface you want. So here's an example. If you then vary, in addition to the distance, you could vary the voltage you're applying. You can get what's called multi-dimensional scanning probe microscopy. So the easiest thing is just to measure the tunneling current as you're moving away also, and that gives you the something that's related to the work function. If you also do changing the bias, you can distinguish different types of atoms, etc. So here's an example on the quintessential oxide surface, rutile 110. Here is the quantitative force channel. Here's the current. And you'll see there's a defect over here, which turns out to be an oxygen vacancy. And there's another defect that shows up over here that doesn't show up over there. If you do a cut along this line here, you see there's some variation in how strongly the tip is attracted to the surface, and it's much weaker where the oxygen vacancy is. That coincides with this point over here, but this defect over here has no effect on how strongly the tip is attracted to the surface. This sort of feature in the tunneling current is typically attributed to a subsurface defect, usually hydrogen, although that's not proven necessarily. This is from the tunneling current decay. You get the barrier height, so you can think of this as a work function variation map. And you can see it's slightly brighter right here, so there's a higher work function. It's hard to pick out where that is. The oxygen vacancy is obvious. That's a decrease in the work function. Okay, so that's interaction of the tip with the surface. As we just heard, surface under reaction conditions is very complicated. So what we want to learn about is how molecules interact with one another. So you can envision there's lots of different scenarios, even if for a simple single crystal metal under reaction conditions. So you could have molecules moving towards an island, you could have radicals coming together, the effect of the step edge, and you can imagine all these different potential scenarios. So this is a difficult problem for theory, which tends to focus on semi-isolated molecules, idealized configurations, or if you get to something this complicated, it's less of a rigorous approach. Experiment, they usually average over many of these interactions, so that's hard to get to just one. So the idea was to see if we could come to a conclusion with this method, the 3D AFM. So what we're going to do, this example is benzene across copper. So what you do is, again, this series of images. In this case, we're only going to go over one line and get closer and closer and closer until we're so close that there's either an attraction that pulls the molecule towards the tip or pushes it away. If you have a force, F dot dl will give you an energy for that. So you can think of it as a diffusion barrier. So here's our data. Here's where the benzene molecule is. This is the vertical distance, and this is the potential energy. So you can see it's attractive, attractive, attractive. You get very close, it becomes repulsive. Through here, this is the vertical distance, and this is the, I believe this one is the, it's hard to see the colors there. These are nanonewtons, so this is the force. So you can see it's attractive back here, and then we're starting to push on it. If we're over here, you can see the force is, you have to get closer over here to start getting that force. You can take this guy and differentiate it, and then you can get lateral forces. And this is the force on the tip. So in this case, when you get over here, the molecule is pushing the tip back that way, or you can think of it as the tip pushing the molecule that way, and then the other side is just the reverse of that. Okay, so we have two benzene molecules next to one another. We're going to take the tip going like that, and you can see that it gets closer to the other benzene molecule. So we know exactly when the jump occurs, so we're this is the tunneling current here. You can see it goes up, and when the molecule goes further away, the tunneling current drops. So you can tell exactly when that happens, and then here's the potential energy, the vertical force and the lateral force. So if we're interested in the pushing, we're interested in this guy here. That's the force. Again, it's on the tip, so we're pushing the molecule that way, and then it's this force right here. So at the jump event, we know how much force we're pushing down with. That's 300 piconewtons. The force going in this direction to push it that way is 30 piconewtons. You integrate over the distance, and you get a diffusion barrier, or something like a diffusion barrier, of 48 millielectron volts. And so we did statistics on a number of molecules, and this happened 12% of the time. Okay, once we pushed it this close, we couldn't get it any closer. So there's a repulsive interaction between these two molecules. And now what happens is we get closer, 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 and the current goes down. That's the push event. And then here's the subsequent event. So instead of the current going down when we get close, the current goes up so that the molecule is moved towards the tip. And again, we do that again and again, moves towards the tip, the current goes up. So we start here, we move there, and then we move there. Okay, so this happened 12% of the time. This happened 16% of the time. What happened the other times? So close to half the time, instead of the molecule moving along the surface, it moved presumably to the tip. And you can see there's nothing there. And in this case, the current also drops. And then no matter how hard we pushed, 26% of the time, nothing happened. All right, so what does theory tell us about this? So in this case, our collaborator, what she did was use this optimization search to get this potential energy surface. And the simplifying factors were that the copper atoms were held frozen and the benzene internal coordinates are held frozen. The copper atom positions held frozen. That's not such a great approximation. But the reason to do that is now you can simulate what happens when you have the tip coming here. So in this case, it's a pure copper tip. And what happens is, this is what we're measuring here. But what she finds is that if we repeat this, the molecule sort of sticks to this tip a little bit. And then when you do additional jumps at that point, you get something that's close to the barrier to move from here to here. So the dragging along the molecule comes pretty close, but this initial thing that we measure, not so close, unfortunately. Okay, so the bare copper tip likes to form a bond to the molecule. The consequence is that the tip lifts the molecule up a little bit when it gets close to it, and this reduces the barrier for pushing. Once you form a bond to that molecule, then the tip sort of pulls it along, and this slip barrier is actually close to the intrinsic barrier. And the results should also be sensitive to the height above the surface, so that comes down to where you sort of stop your approach here. And so we're looking into solutions of, instead of looking at the bare tip, you coat it with a passivating layer. Okay, so that's the case of looking at the benzene molecule. We're also interested in reactions. So we would be interested in what happens as you push a phenyl radical towards another phenyl radical. So the first step in that is creating the phenyl radical. So we start off with this iodobenzene. You can zap that with an electron from the tip and create iodine plus the phenyl radical. So this shows this before that, and you can see it looks pretty symmetric. So this is on one side again, and that's the other. And then this is the before and after. So you can see a little node here after you apply the zap. So now that's an iodine atom, and that's our phenyl radical. And so now you can see this is the before and after, and you can see this split over here. Okay. All right, so what happens when we try to move the phenyl radical? Okay, so here's our initial iodobenzene. Here's our phenyl radical. Here's our iodine atom. And we're coming with the tip like this. And what's going to happen is it's actually going to move further away. So what we find is the first time you move it, it takes a lot of force. And then the subsequent times, it takes much less. So this curve over here is the first time. This is the second time, and this is the third time. So it's a much greater force for the first jump, and then it becomes less and less. So the suggestion is we have an attractive interaction between the phenyl and the iodine. So now we do a whole bunch of DFT calculations, and they don't show this at all. So here's our iodine atom, and then we analyze the energy at all these different positions. Forbidden means if we tried to put this over here, it either jumps further away or reforms iodobenzene. And so the black would indicate that there's an attractive interaction, and the red a repulsive interaction. So for the most part, there's a small repulsive interaction, and there's only a couple of locations where there's a very small attractive interaction. So if we look at what else the molecule can do instead of just moving along the surface as a plane, we find that there's a metastable state where it stands up rather than mostly lying down. And so this opens up a whole bunch of possibilities for different kinds of motions. So once you tilt up, you can tilt back down, but once you're standing up this way, is this the same as going that way? So this has a barrier of only 52 millielectron volts. And that will look like the molecule is moving because the part of the molecule we image is actually over here. So it would look like it would have jumped. The other thing the molecule can do is rotate around this copper atom, and that's a barrier of 169 MeV. And it would appear to jump from over here to over here, so that would give you a 1.81 angstrom jump. This would give you 1 surface lattice constant. If you combine these together, you can go in a circle. And if you want to actually move across the surface, that has a much higher barrier of 322 MeV. And the distinction is being that in this case, we're always attached to that same copper atom. And in this case, we're attached to a new copper atom. So we've actually broken the bonds between the phenyl radical and the copper atom. This would give you a jump distance of 1.81 angstroms. All right, so to summarize this part of the talk, we can measure the forces to displace molecules with this tuned oscillator AFM. We can tell when we've pushed, pulled, or the molecule has disappeared by following the tunneling current. We see a distribution of tip-induced events. The theoretical analysis is that the bare metal tip is not really what you want to have to do this experiment. And if you're pushing, it tends to underestimate the barrier that you would actually, the true barrier. As we push a phenyl radical away from an iodine atom, you see an apparent decay in the barrier to move. However, that's better explained by different types of motion the phenyl radical can undergo rather than an attractive interaction with the iodine. So we've made progress, but we need to go further. And the big thing is we need to control the tip. Okay, so a second example is what we can learn about these copper phthalocyanin catalysts for CO2 reduction to methanol. So a colleague at Yale, Hailang Wang, he's found that these cobalt phthalocyanin catalysts, if you support them in a specific way, and you put specific groups around the edges of this, they're very good catalysts for converting CO2 to methanol by electrochemistry. So here's an example here. It's the same molecule, this one over here, but on different types of supports. This one is without the cobalt atom, and you can see that takes a very large voltage to start to make CO or hydrogen. And the red one's the one we're interested in, on a carbon nanotube, and you can see the onset's much lower. If he looks at selectivity, again, this is the winner. This is CO versus hydrogen, and to make methanol, you need a more negative potential, and then this one's also the winner. Then he finds, he does a series of groups over here, and this is the best one he's found so far, but you get similar sorts of plots where it increases the selectivity to methanol. Here's the overall reaction. So you go to CO2 to CO, and then the CO to methanol, and the counter electrode is the oxygen evolution. So what he finds is that the NH2 improves stability and CO conversion to methanol. He's done some theory on this, which suggests that your key is to understand how strongly the CO absorbs there, and that's the descriptor for your activity and selectivity. Okay, so we want to understand how the COPC interacts with the surface and how that interaction affects how strongly CO absorbs on the COPC and how these are influenced by the ligands. So let's see where we've gotten to. So as a starting point, we've put the cobalt phthalocyanin onto silver 111. Here's a big image with a few, I think it's about 100 or so of these cobalt phthalocyanins, and in STM they look like crosses. The image was rotated 90 degrees, so that's why this direction is this direction. So what he's done is statistics on how these are oriented, and what he finds is that there's basically one orientation with respect to the silver. So these are rotated by 60 degrees, so that's the 3 equivalent directions. There's a slight preference for this one. So it's not entirely random. If it were random, you'd get this distribution only 15% of the time. So this may be influenced by the step direction, which sets up electron scattering that goes parallel to those steps. So that may be influencing and slightly favoring that one. Okay, so many of you have seen the famous IBM picture of a pentacene molecule. So the way they did that is you pick up a CO molecule with your tip, and then you can get something that looks like the molecular structure of the molecule in an NCAFM image, and that's what we have here. In this particular case, it's this FM mode, so this is a frequency image at constant height above the surface. So whenever you do this, if you go back to the IBM pentacene image, the rings are kind of compressed. So this is the benzene ring over here, and then here's the 5-membered ring and the cobalt atom in the center. So we want to look at how the force and ultimately the energy of attraction between the CO molecule and our phthalocyanin varies with where you are in the molecule. So the blue, which is very hard to see, is the reconstructed force curve from the 3D AFM method, and this is a point spectroscopy method, and you can see they overlap. What you'll see is, not surprisingly, so this is the frequency shift over here. It's greatest at the cobalt atom, suggesting your greatest interaction over there. But let's go further with this. I think to get this to play. So we've converted this to quantitative forces. And so here's the video of that. And is this playing? Yes. So that's from very close. And as you can see, that fades away. And as you're far away, the black is the center. And finally, the cobalt atom fades away. Okay. All right, so to go from the measurable in the experiment, which is the frequency, to potential energy and force, here's the equation. The important thing is the integral from wherever distance you are off to infinity. So you have to integrate these curves all the way off to where this goes back to 0. So we do that, and that gives you potential energy over here. And then if you differentiate that along z, you get the vertical force. If you differentiate that in x and y, you get the lateral force. Oh, what happened there? Okay, great. So you can do all these different slices at different distances. So that's again, our original data signal. Here's the potential energy, which isn't all that featureful. So you can see the cross of the molecular shape, and then it doesn't appear to look like much, but we'll come back to that one in a minute. Here is the vertical force. So that's the force pulling you, the CO molecule on the tip towards the molecule. And you can see it fades away more slowly at the cobalt atom. That's going that way. So our closest is this distance over here. Here's the lateral force, which just tells you that if you're over here, it wants to push you away. If you're over here a little bit to the right, it wants to pull you in towards the center where the cobalt atom is. Okay, now let's look at what else we can do. So if we assume there are pairwise interactions, we can subtract out the effect of the silver substrate. If we do that, we get this series of curves. And now we have another video of what happens to the force quantitatively. Click that. There we go. And now we get a little bit more detail. And again, the cobalt atom's a little brighter and then fades away last. So the tail of the curve of the cobalt atom extends further, which is not surprising. Okay, so if we're interested in catalysis, what we really want to know is we have curves that look like this. Well, we want to know the zero energy. And the problem is, again, that would require us to get very close where the tip would likely affect it. So what we've done to try to get a handle on that is to take a Leonard-Jones type of model and fit this to our actual data. And then our adjustable parameters are this alpha, the exponent on the attractive force, our energy, epsilon, sigma, and then there's a offset because we don't know exactly where zero is. Now, if we plot this potential energy minimum across the molecule, what you see is we get this picture like this. So darker is a stronger potential energy. And you can see it's dark in the center. It's actually pretty too dark. You'd expect it to be strongest right at the cobalt atom right there. But there's actually 4 pockets around it that are where the strongest attraction is, the deepest potential energy minimum. Okay, the other thing we can do is we measure the decay of the tunneling current. So that gives us roughly an average of the work function of the sample and the tip. The sample is a constant, so what we get is the work function variation. And so what we see is the cobalt atom over here, which we expect to be somewhat positively charged. So that gives a work function that's slightly lower. And then here's these 4 nitrogen atoms corresponding over here, here, and here. And they appear slightly brighter, though interestingly not equally so. You can get the same information, actually a difference rather than an average, from Kelvin probe force microscopy. So the electrostatic force goes parabolically. And then what you want to do is adjust the voltage so you're at a minimum. At the minimum of that curve is where the electrostatic forces are 0, and the contact potential difference goes to 0. Here you see, again, that's where the nitrogen atoms are, and it's not quite symmetric. Don't know quite why that's the case. And then you can see it's the same features, but we get higher resolution in that scenario. So it's these nitrogen atoms right here that are the bright spots, and those are the same ones over there. Okay, so the elephant in the room is that we're interested in how CO absorbs on that cobalt site. I don't know why that's displaced, but in any case, it wasn't originally. Something happened there. When we pick the CO at the tip, it's actually upside down. So that's the elephant in the room. So our next step is to put the CO molecule on the cobalt phthalocyanin and then remove it by applying electrons here, and then perform what's called action spectroscopy to learn about how much energy it takes to knock that guy off. We want to be able to see how that varies with our electron density around the cobalt atom, which you can adjust by putting different groups around the periphery, and finally with the support. So to summarize, these immobilized cobalt PCs are promising catalysts for CO2 reduction to methanol. The CO adsorption strength is descriptive for activity and selectivity, so that's what we're interested in. There's only one unique adsorption configuration on silver 111. We can see the structure of the molecule if we have a CO tip. If we do simultaneous 3D AFM and STM, we get the 3-dimensional force field, the potential energy surface, the work function variation across the molecule. We can extract the equilibrium potential at every position across the molecule. The strongest attraction, which is around 0.16 EV, is in 4 lobes surrounding the cobalt atom, not directly above it. And the nitrogens in the 6-membered rings are relatively negatively charged, and the cobalt positively charged. First, thank collaborators. Milica does theory in Finland. Percy's at Brookhaven, where we did some of the experiments. Hai Lang is the person who came up with the cobalt phthalocyanide catalyst. Udo Schwartz, colleague at Yale, worked together on the scanning probe microscopy. These two guys over here did the first part of the talk, and he worked on the second one. And we thank NSF for the support. And thank you for your time.
Thank you very much. There is still time for a couple of questions.
Impressive work. I was curious to have some comments on the quality of the substrate to get those nice images, and maybe if you have some subsurface defects. I appreciate the vacancy story at the beginning, but when you have a vacancy, you may have an even larger ions compensating the presence of vacancies, like in Syria or titania 3 and 4. And so if you have a subsurface vacancy, then you may have an effect on the surface, which may be also related to some anisotrope in the imaginary.
Variation.
Yeah, the variation. So.
Yeah, so it's a silver 111 surface, and that's prepared at high temperatures and then cooled. It's a sputtering process, which tends to leave sort of vacancies below the surface, so it's possible. The molecule is also much larger than the silver lattice constant, so it's possible it's not quite symmetrically located, so they're not exactly on top of silver atoms. We're thinking this through. We also have to analyze whether the molecule is slightly tilted. We're still working through that.
Thank you.
Thanks. I have two questions. I mean, first is how long does a measurement take towards your time resolution?
Okay, so the time resolution is terrible. So the second part of the talk with the stacking of the images, that's a 6 to 8 hour experiment. Along the single lines, because you're only doing single lines, that's going to be about 1/64,000th of that amount of time. So that's minutes.
And the second question is the interpretation of what you see. That is, I think it relates a little bit to what you said before. And I mean, you're going to see defects, or you're going to see changes in the forces. And so how certain are you about the origin of what you see in the patterns?
So the first example I showed, the TiO2, the vacancy up in the upper right-hand corner, we're sure that's an oxygen vacancy. The thing in the lower left, so there was a science paper, I think like 2012. They were insistent that it was hydrogen subsurface, and then there were other people who disputed that, so I'm not so sure about that one. The other stuff, why not all the lobes of the molecules are equivalent. So we've looked at more than just that number. More so you can also see it to some degree in the tunneling current. That's a faster measurement. And they're never all four the same. Sometimes you get two that are different. Sometimes it's one that's different. We've also found, and I didn't show this because we're not so sure about this, sometimes the molecules can change state. And that shows up as an unpaired electron on the cobalt atom. And it doesn't stay that way long enough so far to isolate exactly what's causing that. So that might be part of it. That didn't happen in this case because it shows up as a pretty obvious change in contrast. But there are things we don't yet understand.
I have also a question. If you investigate a piezoelectric surface, do you expect to have some changes in the vibrations, in the frequency of oscillation? Did you try to adjust?
Okay.
Yes.
So we're waiting for money to do that experiment. So what we want to do is add lasers to do at the same time tip-enhanced Raman, so we can superimpose the vibrations on top of all this other information. So you should send the National Science Foundation in America your endorsement for that.
Yeah, okay. Okay, so thanks again for the talk, and thanks to all the speakers from this morning, and you are welcome to the coffee break. Hello? 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 Hello, so welcome back. We start the second session for this morning. So it's my pleasure to introduce Luca Artiglia. He's a senior scientist in the Paul Scherrer Institute, and he's doing near ambient pressure XPS. Yeah.
Thank you. I would like once again to join the other speakers and thanks the organizers for this beautiful and unique opportunity to be here. As I tell them several times, they are among my preferred users. I cannot say the preferred users because I must be neutral. And thanks to the chairman to say that I am responsible of ambient pressure photoelectron spectroscopy at the Paul Scherrer Institute. And today I hope to convince you that this technique can be used to characterize the structure-activity relationship in a sort of operando mode. Beautiful movie. It's always the right way to start a presentation. But it's very general, this introduction. It's about heterogeneous catalysts and the fact that reactions in heterogeneous catalysts take place at interfaces. Interfaces are different, solid gas, solid liquid, liquid liquid, so they are intrinsically complex environments. We have different shapes, different compositions, and what is important is that interfaces may change during a reaction. By the way, this movie has been recently published by our group, and it displays how platinum nanoparticles are evolving at a relatively high temperature of 600 degrees C in a mixture of oxygen and hydrogen. So it's necessary in order to establish a structure-activity relationship to make use of what is called operando characterization tools, so to look at systems while they are operating. And ideally, we should also keep being sensitive to the surface or the interface that is the place where reactions take place. What is my business? As I said, I'm a surface scientist, although I am a chemist. So for a lot of times I was working with model systems, but since almost 10 years I came back to my first love, to chemistry, and I really want to try to characterize systems under relevant conditions, relevant system under relevant conditions, making use of photoelectron spectroscopy, which is the technique based on the photoelectric effect introduced by Albert Einstein. If we heat a sample with X-rays and this energy is high enough, we can kick out photoelectrons from a specific orbital. In this case, you see, for example, 1s photoelectron, and its kinetic energy is equal in first approximation to the difference between the excitation energy and its binding energy to the core level. XPS is a surface-sensitive technique because although X-rays penetrate micrometers into our materials, photoelectrons can only escape the topmost layers. And the reason is that they undergo inelastic collision, losing this part of, if not all, this kinetic energy. And so we can only detect a bunch of them, which comes from the topmost layers. This is the universal curve of the inelastic mean-free path. There are most transition metals here, and you see that they are found pretty much all on the same path, which between 50 and 100 electron volts, this is a kinetic energy, shows a minimum. So if we probe our kinetic energy in this range, we can get the maximum surface sensitivity really to the topmost layers, a few layers. It depends on the material, of course. And XPS is also useful to get the composition and oxidation states of an element, because of course our emitter and the photoelectrons are sensitive to the local environment. However, and there's always an however, this has been nicely introduced by Jeroen before, over the years, the fact that XPS has been developed in ultra-high vacuum has established pressure and, as a consequence, material gaps. So this is a nice scheme which shows how surface scientists, yes, it's our fault, created model systems to make some characterizations possible, which were not possible at the beginning with complex systems like impregnated powders and so on. Of course, we can discuss for days that the model system is not a real system, and I agree from several different points of view. But we must try, our mission now is to try to fill both gaps and to try to measure and to make XPS a real operando tool. In this slide, which I like to show to students at ETH, this is just a simplified evolution of XPS over the years. The technique has been developed by Kai Zygmunt, who got the Nobel Prize for that. And he started to work on that in the 50s. In the 60s, he developed the first XPS systems. And it's really impressive that this guy was a pioneer. And he did not only work on ultra-high vacuum systems, which is the most straightforward application. He was already developing high pressure, what they call high pressure systems. Here, this is taken from his Nobel lecture. He was developing rotating disks to investigate liquid interfaces, just dipping such disks in a solution while looking at photoelectron spectroscopy. But at that time, the technology didn't allow him to perform XPS at high pressure in a kind of efficient way. It's only around 2000 that the first prototype of ambient pressure analyzer, new generation, has been introduced thanks to the collaboration between Berlin and Berkeley. And this makes use not only of physical separations as Zygmunt did in the past, it also couples to small apertures, electrostatic pre-lenses, which extract and refocus photoelectrons. This makes possible experiment at relatively high pressure in our cells while keeping high or ultra-high vacuum at the detector stage. But I also wanted to point out that a few years ago, there was a relevant advancement in the technique. The colleagues in Anders Nilsson's group, Peter Ammann, developed measurements up to 1 bar. This is possible increasing the photon energy, working at grazing emission to keep surface sensitivity and coupling what they call a virtual gas cell. So they literally flood the system with a huge flow of gas or gas mixture. And again, we can discuss hours about the validity and the usefulness of such measurements, but that's the story. What I can say is that, again, our mission is to try to fill the gap, and we are doing it quite successfully. What did we do at Paul Scherrer Institute? Well, here there was a project which started almost 10 years ago, and we decided to buy a commercial analyzer and to build our systems based on it. So we developed 3 different end stations which can be connected and disconnected. We can swap from one to the other within half an hour, within 1 day. And each one of them, as I said, is designed to characterize a specific interface. We have a solid gas interface chamber, a solid liquid one, and also a chamber to characterize liquid or liquid gas interfaces with a liquid microgel. But today I will focus on the solid gas interface chamber. It's the system we make use of for heterogeneous catalysis experiments. So we have this analyzer, and we have a cell concept. Actually, it's a cell in the cell concept. We have a small cell, which has been designed, the PSI, which is surrounded by a high vacuum environment. This makes possible experiments with soft X-rays. This is energy range we have available at our beamline. The advantage of having this small cell is that it has a small volume and a flow tube configuration. So we have a gas upstream coupled to a conventional dosing line with mass flow controllers. So people coming from the heterogeneous catalysis community are not scared when they see the gas line. and all the rest is a little bit more scary, but that's life. We can also heat samples and cool them down thanks to different manipulation systems. Thanks to this flow tube configuration, we can dose sticky gases like water or alcohols, as well as incondensable gases. And what is interesting is that we can switch from one gas or gas mixer to another within seconds, doing what is called transient analysis, so time-resolved XPS, to detect, for example, active sites which are hidden in these spectators. But today, the goal of my talk will be to try using XPS to investigate the water-gas shift reaction. We have already heard about this reaction. It's quite important. It's about the oxidation of CO by water to produce CO2 and hydrogen. It's an important industrial process. I don't need to repeat it. I just make the example of fuel cells. You get syngas from steam reforming of methane, for example. And we necessarily need to purify the gas from CO traces, because otherwise CO will poison the platinum catalyst of fuel cells, which are then used to burn hydrogen. What is important is that this reaction is a benchmark for fundamental research in heterogeneous catalysis. There are tons of papers about that. It's a reversible exothermic process, so we have thermodynamic limitations. And we have a well-established catalyst in the industry, one for low temperature, one for high temperature. This is well known from Jeroen's talk before. For high temperature, this dates back quite some time ago. It's based on iron oxide, chromium oxide, and they are coupled in the process. But recently there was interest towards the development of noble metals for the low temperature reaction. And I want to highlight here that although it's a benchmark reaction, there are still several open questions that I wanted to recap in this slide. These are actually only three, which we found out looking at this enormous literature. The first one is, what is the active site for low temperature water gas shift? And here there is a huge debate about atomically dispersed species, single sites if you want, versus nanoparticles. What is the real active site? You see just a couple of high profile papers here. Then second question is about electronic state effects. Everybody sees a size effect, but is it only about the size, or do we also have interaction with the substrate and a dimension or nanostructure effect which plays a role? And what is the modification effect of alkali dopants? These are quite common dopants, potassium, sodium, added to the catalyst in order to improve its reactivity. Is it really impacting on the reactivity? Where is the sodium or potassium going? Platinum, ceria? What are these dopants doing? Well, we try to make use of XPS to characterize WGS in the millibar range. And the first question we asked ourselves was, does it provide relevant results? Again, back to Jeroen's presentation this morning, we see that pressure gap is relevant also for water gas shift. So we decided to adopt what I like to call a holistic approach, which put together several different techniques, not only spectroscopy, which we can perform in the millibar range. This is the mixture we dosed, but also flow reactor tests. And we, on purpose, wanted to reproduce the same reaction conditions we had in the XPS cell. Because we cannot run flow reactor tests in vacuum, we decided to dilute our gases. And we coupled these two important tests with high-resolution scanning transmission electron microscopy and theoretical calculations, which are nowadays, from my point of view, fundamental. Just a few words about the samples we used. We kept the loading stable, 1 weight % of platinum on ceria, and we work with AD and NP samples. AD is the name for atomically dispersed samples. Here you see TM image. Typically, if we don't see anything, it's a good sign, because cerium and platinum, they are very similar contrast in electron microscopy. So the fact that maybe we can distinguish some small bumps is a good indication that we have a high degree of single atoms on the catalyst. Whereas here we have a classical supported nanoparticle sample with a small nanoparticle size. Let's start with the reactivity. Here I show light-off curves, and I want to focus your attention on this first curve here. This is about the 80 sample, and you see that they don't show any CO conversion up to a certain threshold. Above 250 degrees C, we see a steep increase of the CO conversion up to almost 70, 75%, and then it approaches the equilibrium limitation. And interestingly, if we go down with the light off, then we see that the shape changes completely. And if we repeat back, forth and back, the light off experiment, we see that it turns out to be pretty reproducible. So there's clearly an evolution of the system. The question is, what kind of activation underwent this system? So we looked at the spectroscopy performed under the same conditions as I stressed it, as I did in the previous slide. And we start from the top, and we see that at low temperature we see a single peak, well, main peak, platinum 4F with its spin orbit satellite. This is a good indication. It's a 72.8, and this binding energy is in agreement with the presence of, almost unique presence of atomically dispersed species which are cationic. But above 300 degrees centigrade, the peak broadens, and we see that we have several different species. I will come back to this later. So XPS, what is important, suggests that a part of atomically dispersed species sinters, and this is probably in agreement with the bump in the reactivity. This is probably the most important plot until now, because it shows that really performing the experiment in the XPS cell and in the flow reactor gives comparable results. Here you see the CO conversion measured in the flow reactor and the hydrogen evolution signal measured in the XPS cell. We have a mass spectrometer in the second differential pumping stage. And here we ramp up the temperature, which is in the x-axis. We see that up to 250, we have almost exclusively platinum 2+, and then as soon as we start to observe activity, this coincides with the sintering and the formation of metallic platinum. Interestingly, when we go back, when we ramp down at the same temperature, 250, where we didn't observe any reactivity, we keep observing reactivity in fair agreement with the light-off curves in both cases, so reactor test and XPS. So this shows that both techniques are provide comparable results. So we are working in the same environment, and we can really get indication from one technique to another. Furthermore, STEM supports the sintering hypothesis because, again, before water gas shift reaction, we see only a few bumps indicating atomically dispersed species and then nothing. But clearly, after reaction, we see sintering and formation of some aggregates which support the formation of nanoparticles. What happens then if we dope our system with sodium? And here we called our samples ADX and NPX, where X is the ratio between sodium and platinum. So we grew the amount of sodium up to 5:1 compared to the platinum loading. And we see from the light-off curves, but also from the Arrhenius plot, that the catalytic activity decreases as a consequence of sodium doping and sodium increase, as well as the activation energy. The activation energy increases, and the water gas shift rate decreases. So it seems that sodium doesn't give a beneficial effect to our system. Electron microscopy shows clearly that, especially in the AD system, sodium promotes an increase of the average size of the nanoparticles. So this is in well agreement with XPS. We see that sodium at the end of the story promotes the sintering of atomically dispersed species into nanoparticles. And even in the case of nanoparticles, we see an increase of the average size upon doping. Then with all this in mind, we asked us a second question: is it possible to really identify and characterize each single platinum active site and correlate it to the reactivity? Well, we looked back at the literature, and we found some very good inspiration both from model studies and let's say studies on actual systems. Like in this case, this is a model system. It's a platinum single crystal. It was shown that as a function of the under coordination of platinum, we clearly observe a positive shift of the binding energy. This is pretty important for our fitting procedure. The same thing on a model system here. In this case, size selected, it's palladium, but it's pretty similar nanoparticles. When the nanoparticle size decrease, here we go to a 2 atoms particle, there is a positive shift of the binding energy, and this is due to final state effects. So when we have, let's say, a small nanostructure during the photoemission process, we create a core hole, and if the system is not large enough, the hole which is left cannot relax. So we have a destabilization of the system, which translates into a positive shift of the binding energy. And on a real system here, platinum on Syria, it was observed that there was a clear interplay between platinum and Syria at a specific size, I would say within a specific size of platinum. So overall, lower coordination leads to positive shift of the binding energy, and the decrease of the nanoparticle size as well is playing a role. So is it possible, again, to identify platinum active sites based on our spectroscopy? There we made use of theory based on high-resolution electron microscopy. Our friends in Bern modeled several sizes of platinum nanoparticles, and it's very nice that we can get the amount of each kind of site for metallic platinum as a function of the dimension from less than 1 nanometer to slightly more than 2 nanometers. This helped us to fit the platinum 4F peak. You see, we have a shift from bulk platinum to terrace sites, and then edge and corner sites, they show, based on the literature, the same binding energy, but thanks to this model, we could differentiate and we could somehow constrain the ratio between these species as a function of the size of the nanoparticles. And this is an overview of what we obtain. It's really showing a trend as a function of temperature as well as a function of sodium loading. We see that the fraction of different platinum sites, terrace, bulk, edge and corner, evolves with the size of nanoparticles, so with the sodium loading as well as with the temperature during water-gas shift reaction. So there is a clear size-activity correlation that you can see in this plot, and there is a nice correlation between the activity and the fraction of corner sites, which, and we focused our attention, as Professor Fornasiero said before, corner sites have always been, let's say, thought to be the active sites for this kind of reaction. But there is a problem. If we focus now our attention on each single site and we plot the activity as a function of the fraction of such active sites from XPS, we see that the only sites showing correlation are the corner sites. But this correlation plot does not intercept the 0. There is about 7% of these sites based on this model which seems to be inactive. So we need to add more constraints to our model in order to get a better correlation plot. We realized that the reaction is an equation, and in the equation we have different terms. We focused our attention on platinum. We didn't focus our attention on Syria, although we acquired the signals of Syria, because we knew that Syria is not spectator in water-gas shift. And we see a clear trend also in the population of, in the fraction of cerium 3+ as a function of temperature in the water-gas shift reaction environment, and also as a function of the sodium loading. So Syria participates in the reaction. I don't want to focus on the reaction mechanism here. I'm focusing on active sites, but our study was comprehensive. We also looked at the overall reaction mechanism. So we focused our attention on corner sites in contact with Syria. And if we do so, also as a function of particle size, we obtain a pretty perfect correlation plot between the fraction of corner sites and the activity towards water-gas shift only at particle size below 1.25 nanometers. So we call this site CPS. It's quite complex name. It's, let's say, corner sites at the perimeter or the interface with Syria on small nanoparticles. And so CPS are identified as the real active site for low temperature water gas shift. But of course, we wanted to be even more quantitative, and we tried to build a model to evaluate the intrinsic activity of these sites, because of course we have CPS sites, but we have as well other sites which are co-present on the sample and may contribute to the overall activity and activation energy that we measure. So again, this is the plot I showed in the previous slide. This is the equation we used. We started from the assumption that the rate of reaction we observe is a contribution of the fraction of each site times the rate equation, which can be expressed by an Arrhenius equation. This is a quite complex method because we have to combine the kinetic study with XPS, but we had all the data to do it. And then incorporating them into the model, we could see that there is a certain threshold below which we observe a steep increase of the reactivity. And if we focus our attention on CPS, we see that such sites are more than 3 orders of magnitude more active than all the other sites, so they overperform them. Interestingly, here we show the pure geometric effect. So within this range, just taking into account the effect of geometry, of the size of nanoparticle, we would expect to have a constant, let's say, reactivity. But it's not what we observe. So there is necessary, it's really necessary to take the size into account. And then, of course, this goes back to what I showed you a few slides ago, to the literature. The literature clearly shows that there is a dependence between the size and the nanostructure or final state effects that we have in nanoparticles. So to conclude, when we go below this threshold, probably we have electronic state effects which start to play a relevant role and help these CPS sites to perform extremely well at low temperature towards water gas shift. We also did a nice exercise with activation energies. We plotted activation energy from the model as a function of the fraction of CPS, and we see that it correlates pretty well, the fitting and the raw data, with the fact that corner sites have an activation energy around 75, 80 kilojoule per moles. That, this is simply a literature search about activation energies measured in different systems involving platinum for water gas shift, is pretty well in agreement with what the literature shows. So this was a good support to our model, to our conclusions. So I wanted to summarize the main findings of this study, repeating the slide I showed you at the beginning with these 3 important open questions, and namely, what is the active site for low temperature water gas shift? Well, thanks to this study, we could see that it's necessary to sinter, to some extent, atomically dispersed species in order to observe activity at low temperature. Then, what about the electronic state effect? Size dependence is not enough, based on our model, to explain the reactivity. We need to consider final state or electronic effect to explain this sudden change, and they for sure play a paramount role, as well as the support, the interaction of platinum with Syria. We also investigated the modification of alkali dopants. We doped our system with sodium, and it's clear that sodium favors the sintering of nanoparticles under reaction condition, and overall we observed a decrease in the performance of our system towards the reaction. With this, I would like to thank all the people who contributed to this work, but especially Shangsheng, who is a PhD student who defended a few days ago, and Jeroen, who was strongly supportive in all this project. All the people working at the in situ spectroscopy beamline, at the Swiss Light Source, and thank you for your attention.
Thank you very much. So we have time for a few questions.
Thank you very much for your interesting talk. I have a question concerning the effect of sodium that favors the sintering of platinum. How do you explain such effect? And just the second question, probably you can give only the same answer. And do you suppose that there is a strong meta-support interaction between platinum and Syria?
Yeah, good questions. So our hypothesis about the role of sodium is, it's not shown here, but we have, maybe I have it in the back of slides. We observed what happens upon sodium doping, and this is the most interesting result. This is oxygen 1s now. When we dope the system with sodium, we observe a shift of the sodium 1s peak. This is quite impressive, but not so much if we consider the surface sensitivity of the technique. We are really probing the first 2 layers of Syria in this case, because oxygen is mostly coming from the lattice of Syria. But nevertheless, the addition of sodium is enough to shift this peak. This means that we form a substantial amount of this kind of bonds. This is the effect of sodium on the support. I suppose that due to the fact that we form this kind of bonds, we destabilize the interaction between platinum and Syria, thus favoring the sintering of platinum into larger particles. And of course, this is also in agreement with the strong interaction between platinum and Syria, but there is to some extent a competition between the dopant and the active metal in this respect. This is quite clearly showing it. No, the doping was done later on. So we synthesized everything, also Syria, from cerium nitrate, and then in the second step, we added the platinum and the sodium dopant. So sodium, but our results show that clearly sodium goes everywhere. It's on platinum, it's on Syria, but there is of course a stronger effect on that we see on Syria, thanks to oxygen.
Yeah, thank you. Sorry for intervening. So this cannot be just an effect of work function.
Well, not really.
You reduce the work function by adding alcohol.
Because if you look, well, gas phase peaks, they look at the same position as well as the hydroxyls. Okay, also here we also have some water, but this is the only peak which shifts. So if we would have a work function effect, I would expect to have the same shift, which is around 0.2 electron volts for all.
If the adsorbates are on the same surface.
Yes, but we have good evidence that it's the case. Yeah.
Are there some other questions? Okay, if not, let's thank again. So we are moving now from the invited talk session to the oral presentation of younger colleagues. And the first one, Ruxandra. So she graduated from the Illinois University. Then after 4 years postdocs in Germany, then she moved in our institute and she's working surface science.
Okay, so it works? Oh, okay. Okay, so I will present today some of our work in the surface science group here at NIMP in collaboration with the scientists at Elettra, at the Super ESCA beamline at Elettra in Trieste, on the intercalation of carbon monoxide between graphene and the platinum 001 surface. I will first give the motivation for our study, then a few details about the experimental setup that we have at Elettra, and then results about the system, first the first system being carbon monoxide on the platinum surface, and then the other system is this intercalated carbon monoxide under graphene on platinum 001, and finally study with the desorption of the carbon monoxide in the two different systems and conclusions. So why are we interested in these systems? Of course, graphene is a material of interest that continues to be studied widely because it has this great potential for applications, and it's studied in physics and in material science and in chemistry. The 2D surface is of great interest. And for these studies, of course, the actual growth of these 2D surfaces is very important, and one of the, going back to model surfaces, right? One of the very important model surfaces is platinum 111 for the growth of graphene, of course. And at the same time, platinum 111 is also very important for CO absorption. Again, a model catalytic surface. So it's intriguing and interesting to combine these two, right, with the same substrate, the same platinum substrate. And especially because graphene, in this case, if we are able to intercalate carbon monoxide underneath the graphene layer, graphene is no longer an inert layer that inhibits reactions, but actually can act, the overlayer can act as a confinement environment within which you can have CO reactions, and so it acts as a nanoreactor. So for these reasons, we chose these systems. Of course, there are a lot of existing works on graphene on platinum 111, as well as CO absorption on platinum 111, and also on the intercalation of carbon monoxide under graphene on platinum. But there is less information in literature about the platinum 001 surface, even though there's many indications that platinum 001 can be an even better candidate for these studies than platinum 111. So again, we chose these systems, and the experiments were done in our surface science cluster at Electra, at the SuperESCA beamline. It's actually a system that used to be here in NIMP, and we moved it entirely to the synchrotron in Italy, and it's available for general use. And we used both this Cosmos surface science cluster and the SuperESCA end station for these experiments, and the methods employed that are available in these systems are low energy electron diffraction, scan and tunneling microscopy, high resolution X-ray photoelectron spectroscopy, also photoelectron diffraction, and we also did temperature programmed desorption, and we also did near edge X-ray absorption fine structure, but I will talk less about that. And just going back briefly to the platinum 001 surface, I mentioned that there might be some advantages to choosing platinum 001 as opposed to platinum 111, and the main reason for this is the hex reconstruction of this surface, which gives better sites for the absorption of CO. And for the case of graphene, platinum 001 is also advantageous because there's even less interaction between graphene and platinum 001 than for graphene and platinum 111. And I will mention that for the absorption of CO on the surface, we have different types of adsorption sites, and you can see them here. They are atop, so just on top of a platinum atom, or in between platinum neighboring platinum atoms, either bridge or hollow configurations. So this is important to know. Now for our experiments, the structure of the carbon monoxide on platinum 001 samples was investigated. So after cleaning, of course, the platinum 001 crystal, a very, very important step. We investigated both the clean surface and then after dosing CO, the CO sample by lead and by STM. And we can see from the lead that we have the hex reconstruction for the clean substrate, and then we lose that reconstruction, but then we gain this 2x2 reconstruction after dosing CO. And from the STM images, we see for the clean sample, there's these stripes. They're very typical for the platinum 001 surface. And they're actually terraces with this hex reconstruction. And for the CO on platinum, we notice the formation of these islands, right, on the surface once the CO is there. So the measurements after a mild dosage of CO on platinum 001 by XPS, by high resolution XPS, show for the core levels of carbon and oxygen, this region corresponding to the CO molecule, right? If we deconvolute this region, well, it's obvious even without deconvolution, there's two main components, and these two main components are correspond to either to two different types of sites for the absorption of CO. I mentioned these types, the top and bridge and hollow sites, right? So further, doing photoelectron diffraction on the sample, we notice at different angles of emission, we see that the signals, the spectra for C1s and O1s at a higher emission angle, so at a grazing incidence, are preserving the ratio of the intensity, so they stay the same for carbon and oxygen, which is what we would expect from a CO molecule. But then for the carbon 1s spectrum specifically, if we go at different angles, we notice that in normal emission, so this red trace, this red spectrum, at normal emission we have a very high amplification of the signal at the lower binding energy. So this means that the lower binding energy component is affected strongly in diffraction. And to further explain or to further show this, illustrate this, if we look at the graphs for the intensity versus emission angle for oxygen 1s and carbon 1s, we see that indeed for, this is just a multiplication of the lower signal by 2.5, so the second row. We see that for the oxygen, indeed, there's barely any effect in XPD, so no forward focusing. This is due to the fact that the oxygen is on top, so there's no further scattering from any other atoms on the way to the analyzer. And then there's significant amplification as mentioned, so forward focusing for the different carbon components as opposed to the oxygen. So this is attributed to the fact that in the case of the carbon, which is below the oxygen, we have different tiltings of the molecule. So to assign these different components to the different types of sites that I mentioned to determine which type of site corresponds to which component, we look at simulations versus experimental data, again in diffraction, and we see that the best assignment that we can get is for the lower binding energy component. We have we have the hollow type of site. And then for the higher binding energy component, we have a top configuration. So then going further to the other system with graphene on platinum and then intercalating carbon monoxide underneath. To show this intercalation, we can look at both the STM images. So first we have carbon on platinum 001, and then the intercalated carbon underneath the graphene. And we see the islands that I mentioned before, and then after graphene and dosing carbon underneath, or dosing carbon and then the carbon intercalating underneath, we see graphene. The graphene is actually covering the same types of islands. And from the XPS data, these were multiple experiments done with different dosing of different thicknesses of graphene and dosing CO on top. And the important information to, maybe it's not exactly visible which spectrum is which, but the important information is that we see a shift in this is the graphene peak, right, at the lower binding energy at around 284 eV. And we see this shift of approximately 0.2 eV to lower binding energy when we have the intercalated carbon monoxide. And then for the region with carbon, with the CO region in the carbon 1s spectrum, we see a slightly lower, here it's a slightly lower intensity for the intercalated carbon monoxide. So we conclude that there is a decoupling of the graphene after dosing CO, and the CO is underneath the graphene. And this just shows a further analysis of this happening, a comparison here of the graphene signals between different thicknesses of graphene, and also once the carbon monoxide is intercalated underneath, we have this shift that I mentioned, approximately 0.2 EVs. And then if we look at the carbon and oxygen shapes of the spectra for the intercalated carbon monoxide samples, compared to the just carbon monoxide on platinum, we see that they are similar, and we also can subtract this this spectrum from the final spectrum, and we can do a further deconvolution here. Basically, the message is that they are more or less similar, so we expect that the carbon monoxide behaves very similarly underneath the graphene to when it's just on the platinum surface. And finally, the experiment that I'm going to show as a final discussion is that for temperature programmed desorption of the carbon monoxide for the carbon monoxide on platinum sample, we noticed that the desorption happens in 2 steps, and basically the total desorption occurs at around 260 degrees C. But then if we go to the case with graphene on top of carbon monoxide on platinum, we see that it's a very different situation, and that the total desorption doesn't happen until around 900 degrees C. So as a conclusion, this means that the carbon monoxide is much more stable under the graphene. And the conclusion, we are still working on these results. There's a lot of complexity in terms of how the carbon monoxide is actually positioned underneath this graphene layer. And so we also have, I mentioned that we have NEXAF's results that we are trying to make sense of, and a lot of details that we are still attempting to explain. But these were basically the results that I wanted to present.
Okay. Yeah, okay, thank you much. Hope you enjoyed. Thank you for this very nice talk. Yeah. So a few questions. There is time.
Can you go back to the slide where you show this diffraction effect?
Sure. Which part?
I
This
think
or further?
the different angles. I think the next one. Yes. I just wanted. Yes. Could you explain more what do you mean by because with photoelectron diffractions you have a lot of constraints. You need to be in the right azimuthal angle to have the forward scattering, and
Sure.
if you have, I can imagine if you have adsorbed CO, there is not a double layer. So, what kind of scattering do you see? You can see carbon-oxygen scattering, forward scattering,
Yeah,
but
yeah. It's
because what I see there is angle resolved analysis, which usually is like you change the surface sensitivity of the technique. Indeed, you have some peak at 284, which is probably some dirty on the sample, and you see that it's more at the surface. Yeah, exactly here. You
yeah.
see
This
that it's
is
more
this,
of the,
this is
or it's
okay.
boudoir reaction. I don't know, yeah, if you can comment about this, the slide of the scattering, what was the principle you used?
The idea is indeed that we have scattering happening. I even mentioned that there is scattering given by the oxygen on top of the carbon that happens in the case, and it's much more pronounced in the normal incidents because and at the lower binding energy. Yeah, sorry, normal emission. And it's at the lower binding energy component, which is this one that corresponds to the hollow sites, where we expect that the carbon monoxide molecule is standing up perpendicularly. So this is our hypothesis, and on the other sides, on the top sides, we probably have various tiltings of the carbon monoxide molecule, and this smears out the effect basically. So we don't have this, so for the higher binding energy component, we barely have any difference. I don't know if this answers your question, but that's basically.
Maybe I would also investigate the carbon to oxygen ratio for each component. This might be interesting.
We are
different
definitely
angles.
looking at that, and I think this is a very big problem that we've been discussing for, it seems like, years now.
We also proposed a model in which the oxygen is going
Yes.
towards platinum, but
This was a standing hypothesis for a few
It
months.
was really there.
But,
up to now, there were 8 versions of the manuscript that
Yeah.
were elaborated. Yeah, okay. So normally, if the molecule is just sitting perpendicular on the surface with carbon and oxygen, you should have the same forward focusing effect in normal emission.
Yeah.
Now, if in one site the molecule is vibrating or is just disordered or is just tilted, then for one site this forward focusing effect will be smeared out. So this is what is showing this graph at the end.
And in terms of the ratio that you said, we're basically saying that based on these results, that at the grazing incidence we have the same ratio. We will need to base any intensity calculations for in terms of the quantities of the molecules
It's not clear.
on
It's 70
the
degrees.
oxygen.
It's really very grazing.
So on the oxygen, not on the carbon, because of these additional effects that happen on the carbon, clearly. So.
Okay, are there other questions?
What is your working hypothesis of the sites that cause this CO to stay until 900 degrees?
Working what? Sorry?
Hypothesis. Why do you think the CO sticks until 900 degrees? What is your working hypothesis? Before it's desorbed.
How we explain that it sticks?
Correct.
Under graphene. Yeah, basically because the graphene confines it, and as opposed to when it's we have graphene covering in it. Yeah. Yeah. You can go back. It's very high.
Right, so there's questions about how it gets there as well, but we'll leave that for later discussion. But you said there's basically very little influence of the graphene on how the CO is absorbed. Do you see, you think that some of it's tilted? Do you see, the simple explanation is the graphene would be kind of pushing it down, so perhaps like to tilt more? Do you see any evidence that it's tilting more or about the same?
Given the fact, I think, given the fact that we do see some additional components, in the case of the graphene cover, right? We do expect that there is some tilting. I think at different points we made some estimation of distances, but I think our main conclusion was that just the graphene was decoupled and it was actually a greater gap. So not necessarily pushing it down, but for sure some additional tilting of carbon monoxide as compared to when it's just really
And I guess just one follow-up, this CO that stays to very high temperature, is it look any different in the XPS?
I don't think we know this. Do we know this? No. At high temperature. I don't know.
Well, you heat it up and then you can cool it back down. The CO that's left doesn't look any different.
There's nothing left, I think. That's the,
Well, let's say you heat it to 800 C. So there's,
I
so
don't
the
think we
only,
tried
you have
this.
only the small amount.
No, I don't think we tried this. So take it to a lower temperature and then measure it. True. We did do time resolved measurements as we were heating.
There's nothing unusual about the stuff that stays.
No, I don't think so. I don't remember. I don't remember. Yeah, there being something obviously different.
Yeah, okay, so sorry, we have to stop now because I was so tempted. I'm inviting now the next speaker. Kolbe from the Technical University from Zurich. Please.
Good. Hello, you hear me? Hello everyone, I'm Claudio, and for the next 15 minutes we're going to talk about the surface chemistry by operando SCM XPS. And traditionally there are two methods to study chemical reactions. The first one is a trial and error, in which we synthesize a sample, we make a change, and then we study its effect. But then we have to do it over and over again until we get what we want. And then that's the problem, because you have to repeat those studies and those analyses And this can happen either 0 or thousands of times, and depending on the luck. So then there's a different approach, the operando type, where the sample and the change and the effect are studied simultaneously, and then we can correlate the links between them. But then why operando is then the exception and not the rule? And just to show you that, I prepared a small visual representation of those. So this is the instrument that exists at the moment. It's a standard, so to speak, instrument. And then this is what is predicted to be made. So it's a similar version, nicer one. But then actually for operando studies, this is what we need. So we need something which looks very similar, but it's completely different on the inside. And then the point is that this doesn't really exist at the moment. And then for chemical reactions, as we saw earlier today, they underlie reactants. They go absorption, activation, reaction, desorption, and then products. And everything is driven by energy, this being a cycle. Then, if we look at the tools that we actually need, as I said before, and this is from a paper from one of my colleagues, we see that if we plot the length scale and the time, if we probe from meters to nanometers and from picoseconds to days, with the best tools that we have, we see that the active site is not available to study, cannot observe it directly. The catalytic cycle the same. Molecular transport and intraparticle transport are not accessible. Then the operando regime is left, as we can see is here. It's not very convincing for us, right? So it's a bit disappointing. And then to show it better, this example, let's take the opposite, where our detectors are better than the process that we're looking at. So for example, here, I'm going to show you a movie from the opera in Budapest. And then our detectors are huge. So they're 500 megapixels, the eyes, and the movie is 0.2 megapixels. So we oversample a lot. Frequencies also. So we should be able to see what is the clapping frequency of those people. Just to make this exercise, I'm going to play the movie. I hope the audio will be synced as well. So then you will see the clapping, and you should guess what is the clapping frequency of those people. So I'm not going to talk, but I would like to pay attention to this video and to the audio. It's quite tough, right? And again, we are oversampling. Our detectors are way better than the process. But then one trick that we can apply is that to turn the feedback loop on, to study them operando, and then to let the people clap and synchronize. And then I would like to play the same movie with the synchronization turned on. So now I think it became easier to guess the clapping frequency. And just to prove you that, if we plot the audio signal, this is what we looked at in the beginning, no synchronized, and then when people start to synchronize, we can see those clapping events. We can see each clapping here of the people because they were synchronized. So with our detectors on our ears and eyes, we can see what is the clapping frequency. And the answer is actually 2 Hertz. What is this important? We can do the same thing in catalytic cycles. So we can synchronize the catalytic cycles. We can couple the individual oscillators because the catalytic cycle oscillates, right? So then the oscillatory reactions in heterogeneous catalysis are quite wide. They're seen in a lot of reactions, for example, in supported and non-supported catalysts, from noble to non-noble metals, from single crystal to polycrystalline to zeolites. So they're quite widespread in pressure from UHV to above atmosphere. And there are 3 main types. I'm going to talk about just one today. First is the oxidation part of reactions, reduction, and decomposition of different compounds. And they all oscillate. At the moment, there are around 77 chemical reactions that oscillate. The most well-studied are the hydrogen, CO, and NO because they're model systems, because of very narrow product distribution, hydrogen forming water, CO, CO2, and NO, NO2. But those are model systems, and then if we want to delve into the processes, then we will need to study something which is closer to a normal chemical reactor, which is, in our case, ethylene. So from now on, I'm going to talk about ethylene oxidation to syngas, or partial oxidation, in which ethylene reacts with oxygen over a nickel foil to yield hydrogen and carbon monoxide. And what I'm going to show you are some SEM movies, in which you're going to see here the movie, mass spec data, and here's time, gas, temperature, and the scale bar. This is how an SEM image looks like. And as you can see, it's a polycrystalline foil made of single crystalline domains. For example, here, single crystalline domains. And here's the mass spec data. I'm going to play the movie, I'm not going to talk, but then I would like you to check what is happening in this oscillating mode. The surface of the catalyst will change. It will turn from this metal to an oxide, and then you will see this in the image and in the mass spec data. So here's the movie. And then the reaction follows. So the gas phase follows surface here. You see the hydrogen goes up and down. Water stays very low because it's very selective. And then ethylene goes up and down with oxygen. So reactants are consumed, products are formed, and the surface follows them. This is done in a 10:1 gas ratio between ethylene and oxygen. Okay, so seems complicated, and it quite is. The reason why I stopped the movie here is that, as you can see, some grains behave a bit different from the others, and I'm going to talk about those later. But please keep in mind those two ones. This one, which looks like a Nike shape, and the other one on top. So if we take in a bit more detail, we can divide this movie into 4 sections: the active region, the inactive region, and then because of those oscillations, because we can couple them, we can start and stop the reaction many, many times by not changing the gas, because by the reaction itself, we can study also the activation process and the deactivation process. And this is possible because we can synchronize the reaction. So the active region from the SEM data, we can observe that the catalyst is characterized by a metallic state, with a very low orientation contrast and very low secondary yield. The image, so to speak, looks black and dark. We can see grains. And then everything is correlated with the mass spec, where hydrogen is produced and ethylene and oxygen are consumed. We did the same experiment in the XPS beamline at the Paul Scherrer Institute. And then we did this time resolve in situ reaction. And then what we can see here is that for nickel, it confirms that this is a metallic state. And then the interesting part now comes with the carbon and oxygen spectra. In the carbon 1s, we can deconvolute the spectra is carbon monoxide and other carbon-containing species on the surface, while the surface is active. And then in the oxygen region, there is carbon monoxide, OH, and are the main surface species when the catalyst is active. And then when the catalyst is inactive, first of all, in the SEM, we lose all the grain orientation contrast. We don't see any grains at all. This is the first indication that the surface is oxidized. And then the fact that the image is brighter indicates that it's a higher secondary electron yield because of the oxygen absorbed on the surface. Mass spec data is in correlation, so hydrogen is low. See, ethylene and oxygen are not consumed anymore, so they're high. The interesting stuff is also in the XPS, where the nickel shows a binding energy shift because it transforms to an oxide. The carbon 1s signal is below the limit of detection, so the carbon species are gone completely. And then the oxygen shows just the oxide phase. Then for partial conclusions, which at the moment probably seems very easy, the active region is metallic nickel, which if you look with an optical microscope is black, is covered with oxygen and carbon containing species, and the inactive region, which you look with an optical microscope, is green, and then it's the oxidized nickel. But then if you pay attention to the mass spec data, this happens when, so the transition between metal and oxide happens when the oxygen is at the minimum. And then it reduces when oxygen hits the maximum concentration. This is quite interesting, and it's been observed before in literature, but not commented, and I like to dwell on that. So we need to look at activation process, what it happens. And first, what we can observe from this image, the reduction process is not localized. You can see we have different patches of this black stuff, which are the metallic patches. It's not localized, they happen everywhere. And the products that are detected during the active phase are continuously generated. So this is, the reaction is a continuous process that goes on the surface. It's not because of one monolayer. And if we look at the time resolved data, we see that, for example, for nickel, we observed binding energy shift. So the peak goes to a positive shift, which is indicating the oxidation. And then, very interesting for carbon, the amount of surface species constantly decreases over time. So the surface species actually protect the surface. Carbon monoxide and other source species protect the surface against full oxidation. And then for the oxygen, it's the same here. During the inactive phase, the oxygen signal is very high because of the nickel oxide on the surface. Then for the activation process, there is a difference here because, as we can see here, the oxidation, we can see it's localized. The white stuff is the nickel oxide. It follows the grain. This grain follows here, same here, and same here. So that's the first difference. The oxidation process is localized. And also, furthermore, the concentration of those carbon species constantly decreases. Then, to take advantage of the SCM spatial resolution, I plotted those grains in red, which behave a bit differently, and we need to understand why oxidation happens where it happens. So for that, we did EBSD mapping, in which we can determine the surface orientation. And for those two grains, we can see that those one in blue, which behave differently, the point where the oxidation starts, the activation process starts, are the 1-1-1 orientation, while the rest is mainly a 1-0-0. So they're different from the rest. They behave different from their surroundings. And just to point that, here you're going to see the movie of one of these cycles running, and the behavior that you're going to see here is the black part of the image, the metallic species, which they first hit this grain, they don't cross the border, which is very interesting. So they don't cross the border, then on the second attempt they cross it, but the propagation speed is very different. As you can see here, they just go on and on, but this stays stable. Then here, interesting stuff is that you have an inverse behavior. At the moment, you see this grain at the beginning was reduced and the rest was oxidized, and now it's reversed. So the behavior is different. The sticking coefficients of species on the surface is very different for different grains. So as a conclusion, with a scanning electron microscope, we have the information of where it happens and when it happens. And then from NAP-XPS, we know when it happens and what happens on the surface. And to summarize the catalytic activity, the active nickel island converts ethylene to syngas, while for the surroundings, the nickel oxide is inactive. Then, if you have a question about the steady state conditions, this is how it looks if you look at the steady state conditions. So when the catalyst doesn't synchronize anymore, when the catalyst cycles are not synchronized. Every point here is oscillating on its own. And this is how it looks. It's very fast. I'm going to slow down the movie. And then what you see here is that they don't form waves anymore. They form spirals. For example, here, if you slow it down enough, you can see they form spiral waves. It's quite interesting. And then if you look at the MS data here, this is the active, the steady state conditions. But actually, might be that all the catalysts are oscillating in a way, but we cannot observe this because we don't have the spatial resolution that we can get, for example, in this case, by in situ SCM. So they form chemical waves that are present on the surface, and they change the very fast chemical state of the surface, which modifies also the distribution of the active sites. And for that, I'd like to thank the group that I'm in, so my colleagues from Scopem, Milivo and Marcel, that helped me during the beam time, and also for the development of the instrument, Luca and Jeroen from Bokovan Group, and also Mark Fillinger, and also my colleagues from Scopem and SETEC. With that, I'd like to thank you for your attention, and I will take questions.
Okay, thank you very much. Very nice. Okay, so open for questions. Everything was clear.
Actually, not really a question so much as a comment. I want to congratulate you. It's a beautiful study. I work mainly with oxides, and on oxides we see very strong relationships between reactivity and crystal orientation. And I've talked to my colleagues who work on metals, and they told me, no, there's no big effects there. Shouldn't bother looking. And so I just was very pleased to see you refute those comments, because I've always suspected there must be orientation effects on metals too. Beautiful work.
Right.
Okay, other appreciations? Okay, if not, thank you again, and enjoy the lunchtime. Yeah, okay, so we go to lunch now. So, yeah, 1 hour, we'll be back. Okay.
Okay, hi, welcome back. It is my pleasure to be the chair of the last session of this day. I hope you enjoy your lunch, and I hope the next speaker will energize us with knowledge in relationship with fuel cells, electrocatalyst, and water electrocatalysis. So it is my great pleasure to introduce you the first speaker, Dr. Andras Tompos, which is the director of the Institute of Material and Environmental Chemistry, and he will present us in the next 30 minutes many outstanding results that he achieved. Please.
So, thanks, Stefan, for the introduction, and thanks for the organizers, Michaela, to invite me. And in this way, I got the chance to show some of our results, recent results, mainly related to catalysis, but I will also touch some other material science issues. So there are several fuel cell technologies, and the main difference between these technologies rely on the electrolyte they use. Some additional information will be provided by Professor Deckel about anion exchange fuel cells in the third presentation today. So here, what our expertise is in the Institute of Materials and Environmental Chemistry, we developing electrocatalysts for proton exchange membrane fuel cells. On the anode, on the negative electrode, hydrogen is activated and the protons crossing the membrane, and on the opposite side, it meets with the electrons and oxygen, and finally the product on the cathode side is water. So as I mentioned, we developing electrocatalysts mainly, and the main challenge is decreasing of platinum demand, but also there are such issues such as, for example, CO tolerance. In case of reformates, carbon monoxide is produced, and the water gas shift reaction and the preferential oxidation of CO and other techniques probably not sufficient enough to provide a completely carbon monoxide free hydrogen stream. And in this case, the CO tolerance of the anode side has high importance. Additionally, obviously, we have to focus on bipolar plates and proton exchange membrane. This is, I mean, the whole reactor, whole electrochemical reactor has high importance, and all the components in this electrochemical reactor should be developed simultaneously in order to meet all the key performance indicators. For example, which are listed here for fuel cell electric vehicles. So obviously the cost of the system can correlate with the production number reversory, and also can correlate with the platinum content. Power density have to be improved, area density have to be improved, and the lifetime of the system. So first, I will speak about electrocatalysts. So as I mentioned, we have to reduce the platinum content, have to increase corrosion resistance, increase the conductivity of the electrocatalyst, CO tolerance I already touched, and selectivity hydrogen oxidation reaction. It's important when during the startup and shutdown processes where oxygen can be present on the anode side, on the negative electrode as well. And in this case, in order to avoid oxygen reduction reaction on the anode side, we have to develop catalysts that are selectively converts hydrogen and does not convert oxygen. And obviously, because of the sluggish reaction kinetics on the positive electrode, high activity of the cathode electrocatalyst is an important issue. So we try to touch all these issues with development of a composite support. The central point is the oxophilic dopant, what we want to incorporate into the rutile lattice. And with this oxophilic metal, we want to achieve the CO tolerance. There should be an interplay between the platinum and the oxophilic metal. According to the related art, it can be a bifunctional catalysis, so the oxophilic metal can provide the oxygen, and in this way, in adjacent position with the platinum atom, the carbon monoxide, which is adsorbed on the platinum, can react with the oxygen adsorbed, or hydroxide absorbed on the oxophilic metal. Another advantage of incorporation of oxophilic metal into the lattice of rutile can be the improvement of the conductivity. The rutile, titanium, is actually a semiconductor, and obviously it has to be conductive, electroconductive. The addition of oxophilic metal dopant will increase electric conductivity. Obviously, the electric conductivity will not be as high as in metals, but somewhat higher. And in order to further improve electric conductivity, carbonaceous materials are also added to the composite. Other role of the carbonaceous material is that it should be a good hard template. It should have good high surface area. So beyond the high electric conductivity, it provides anchoring sites for deposition of the mixed oxide, and while distributing the mixed oxide in this way, providing good deposition anchoring sites for the platinum active metal. So these are the role of the components I already mentioned, so listed here. What I would like to probably emphasize that an optimal ratio of the mixed oxide and carbon should be fine-tuned and should be somehow improved. And we came to the conclusion that it should be high enough in order to provide high specific surface area and high conductivity. Here are some results about the carbon monoxide tolerance of our composite materials. On this left side picture, there are voltammograms or linear sweep voltammogram. Previously, the electrolyte, this is taken in a 3-electrode electrochemical cell, and the electrolyte is previously saturated with carbon monoxide, and we implemented a positive forward polarization and investigated how the current is changing. And when the composite supported platinum catalyst is used, we can see onset potential at 50 millivolt or between 50 and 200 millivolt. So already some current appears in the presence of our catalyst, and it means a low over potential when the carbon monoxide oxidation can start. And here, as a comparison, you can see the RH type of carbon monoxide tolerant electrocatalyst, the carbon supported platinum ruthenium, and here the carbon supported platinum catalyst. So in both cases, the catalysts are less CO tolerant than hour. In this other linear sweep voltammograms, we can see simultaneous electrooxidation of carbon monoxide and hydrogen. So the electrolyte was saturated with this mixture, carbon monoxide and hydrogen, and again a linear sweep voltammogram was taken, and we can observe a significant current density at low potentials, low positive potentials, which means that not only the carbon monoxide but also hydrogen is electrooxidized. In order to prove that, because these are the techniques, three electrode techniques is exclusively for investigation of electrocatalyst. In order to prove that it works in a whole reactor, single cell tests have been taken. And you can see that with pure hydrogen, we have a good performance. And addition of 100 ppm carbon monoxide in hydrogen stream led to a drop in the performance in each cases. However, over our composite supported catalyst, this performance loss is smaller. The decrease in the performance is smaller than in case of R-type platinum, ruthenium, carbon monoxide tolerant catalyst, and carbon supported platinum catalyst. On this slide, on this picture, you can see that how the switch between the incoming gas flow affects the performance. Upon addition of a reformate with 25 ppm carbon monoxide, there is a drop in the performance, but still we can measure some current density. And when we switch again to hydrogen, the current density can be recovered fully, completely. So, as I mentioned, the incorporation of the molybdenum into the rutile lattice has high importance. We have to somehow prevent leaching of molybdenum in order to avoid poisoning of the membrane. So, but in order to incorporate molybdenum, we came to the conclusion that we have to provide rutile structure. So it's important to have rutile in order to incorporate molybdenum, and the rutile can have some molybdenum content, but not too high. As emerges from this slide, we add 20% of molybdenum, then we can see exclusive formation of the rutile. However, with increasing molybdenum content, we can see additionally molybdenum oxide appears also. So not all the molybdenum can be incorporated in this case. In order to provide the rutile structure, we have to fine-tune the sol-gel method for the synthesis of our materials, and we came to the conclusion that the good dopant incorporation, molybdenum incorporation or tungsten, can be found only if the rutile nuclei are formed prior to addition of the dopant. So there is high importance of aging. 4 days aging we apply. Even after 2 days, we achieve a high rutile formation, but for sake of to be on the safe side, we apply for the aging in order to have a complete transformation of the sol to a rutile nuclei. Obviously, depending on the components, for example, the oxophilic dopant or the carbon species which are added, the recipe has to be improved, has to be fine-tuned. For example, here on this slide we can see that in case of tungsten is applied beside the high temperature treatment, we need a reduction as well at 650 degrees C. In case of molybdenum, the formation of the solid catalyst is enough to have a high temperature treatment in argon. This is about what the role of the carbon. We have functionalized black pearls and the natural, or I would say the parent black pearls, and these numbers here, 25, 50, and 75, just indicate how much in weight percent the ratio in between the black pearls and the composite oxide. And with increasing carbon content, the mixed oxide to carbon ratio detected by X-ray photoelectron spectroscopy became quite so there is a good accordance, a good agreement between the nominal value and the experimental value. The same holds if we investigate the surface composition with the bar composition. Surface composition is investigated by XPS and the bar composition with ICP, and these values become approaching each other, approximating each other with increasing carbon content. So we came to the conclusion that the carbonaceous material behaves as a good hard template, leading to homogeneous distribution of mixed oxide particles, layers over the carbon. And according to these pictures, good proximity between platinum and molybdenum could be reached, which is important from point of view of CO tolerance. How we investigate the aging with this cyclic polarization technique. So several times, more than 1,000 cycles, with the forward scan and the backward scan is investigated, and we measured the electrochemical surface area, which is this peak between 50 and 250, 300 millivolts. And as emerges from this slide, with a high ratio of black pearls or functionalized black pearls within the composite materials led to smaller loss in the electrochemical surface area in comparison to other materials and in comparison to the reference carbon-supported platinum catalyst. Yes, the previous slide is complemented with other carbon materials. The Vulcan was also used as a reference, and over the Vulcan supported mixed oxide, I mean the composite with mixed oxide and Vulcan led to a higher loss in the electrochemical surface area. What I would like to say on this slide that we have to compare hydrogen oxidation reaction activity with oxygen reduction reaction activity over the composites, and the hydrogen oxidation in hydrogen oxidation reactions almost so I would say each of our composite supported catalysts outperforms the reference one, while in oxygen reduction reaction the functionalized black pearls, the catalyst with functionalized black pearls showed a very weak oxygen reduction reaction activity. And from our point of view, it's an excellent result because it indicates that this catalyst is selective or more selective than the carbon-supported platinum catalyst towards the hydrogen oxidation reaction. So it's a good catalyst to be an anode, and probably during the startup conditions, it can prevent oxygen reduction reaction on the anode side. So this is just the summary what I spoke about, and I would like to skip because the time is short. And I would like to show something about the molybdenum-platinum interaction. We prepared two types of electrodes. Here you can see a cyclic voltammogram on an electrode where single crystal platinum was used, and molybdenum is deposited electrochemically onto the surface of platinum, and you can see that the typical peaks, which are characteristic generally on a composite supported catalyst, can also be seen. So here are the hydrogen desorption peaks. This is this redox pair belongs to the molybdenum oxidation reduction +5, +6, between +5 and +6. You can see also on this cyclic voltammograms. So I would say that the cyclic voltammograms, both electrodes are quite the same. What we can see difference is if we investigate X-ray photoelectron spectra of different materials. If we use the single crystal electrode, the model system, the platinum model system, then we can see that treatment different time, different temperature in hydrogen results in reduction, almost complete reduction of molybdenum to molybdenum metal. It means an alloying of molybdenum with platinum. In contrast to this, in the case of composite supported catalyst, we can see some reduction of molybdenum to metallic state, but after air exposure, the catalyst is completely recovered, and the original, almost the original state can be recovered. And in case of model system, a single crystal platinum system, still after the air exposure, part of the molybdenum remains in metallic state. So it's just indicates that the catalytically important molybdenum species do not cover the surface of platinum particles in case of the composite supported platinum catalyst. And the catalytic role, they play the catalytic role as built into the support. So there should be interfacial site, solid-solid interfacial site between the composite support and the platinum, where the molybdenum is in adjacent position in atomic scale to platinum. So we selected a catalyst as parent one. This is doped with molybdenum, and the concentration of the carbon support to mixed oxide was 50-50, and it was reduced at 250 degrees C. This is quite a mild condition in hydrogen, and we can be concluded according to the XRD that there is no increase in the crystallinity. I would say there is no agglomeration of platinum nanoparticles observed, which is also supported by the transmission electromicrographs and histograms as well. So here we can compare the nominal composition with the experimental one. Even in the previous slide, it was indicated that we always measure with XPS significantly higher amount of platinum on the surface. It's not a surprise. It's a surface species, the platinum. It's generally in this amount, 20% covers the outer surface of the catalyst. So, and there is only a small difference between the parent and the catalyst that is treated 250 degrees C. It can be a combined effect of encapsulation and sintering. But according to the previous slide, we suggest that this is encapsulation. What is a bad thing that the carbon to mixed oxide ratio is instead of 50-50 becomes 20-30, indicating that bad dispersion of the oxide phase. So this experiment should have been performed with significantly higher amount of carbon, but now this is the results what we have right now. And the molybdenum to titanium ratio is close to the nominal one, and the nominal is 1 to 4, and there is no too many changes. So you can see a comparison in pair between the parent and the reduced catalyst, the XP spectra of these samples. This is the as received state. They are quite similar. And after exposure to hydrogen in the XPS chamber, already we can detect some metallic molybdenum in case of the hydrogen-treated catalyst, and further increasing temperature of hydrogen exposure, the fraction of the metallic state molybdenum increases. So we can conclude that the molybdenum species can be easily reduced in case of the hydrogen-treated catalyst, and probably we can observe migration of molybdenum species onto the platinum particles. In contrast to this, the parent catalyst does not lead to molybdenum platinum alloy. So here are the models for the two systems. This is for the parent catalyst, and this is for the hydrogen-treated one. So according to our model, the molybdenum migrates at this temperature to the surface. And the electrochemical measurement says that not too many differences between the parent and the hydrogen-treated catalyst. Some loss in the electrochemical surface area upon the hydrogen treatment is observed, which obviously due to the encapsulation and the migration of molybdenum oxide onto the platinum surface. Nevertheless, it has some positive effect on the stability. So in case of the hydrogen-treated catalyst, the loss in the electrochemical surface area is smaller than in case of the parent catalyst. So this is the summary, and I think there is no time for membrane things. So I would like to say for your thanks for your attention. And
Please.
So thank you very much for your talk. My question is not strictly related to the electrochemical activity, but is just related to the preparation conditions and the role of the rutile phase. If I well understood, you reported that you prepared titanium by hydrolysis sol-gel procedure starting from titanium hydroxide. And in acidic conditions, you get after aging only rutile phase.
Exactly.
And is it stable even after high temperature treatment,
Yes.
the rutile? And it is important to have a rutile phase for the electrochemical activity.
Yes, yes. According to the related art, we came to the conclusion that yes, it's important that we should have rutile, and anatase cannot incorporate in such a high amount of dopant into the lattice substitution sites.
Okay.
So it's, as soon as we have rutile, as this is the thermodynamically stable form of the titania, any treatment just keep this structure.
Okay, but excuse me, is the rutile stabilized also without any tungsten or molybdenum, or just in the presence of the dopant?
The challenge is just to have the rutile structure in the presence of any contaminants. Without contaminants, so without, I say contaminants, molybdenum, tungsten, but without this foreign ions, the formation of rutile is even more easily. There is one exception if we add tin. In case of tin, this is, I would not say it's an incorporation into the lattice size, but it's a simultaneous formation of the tin oxide, which has a similar structure as rutile. So there is a growth of nuclei, rutile nuclei, over the titanium oxide. So in this case, the rutile formation is easy.
Okay, thank you.
Thanks for the nice presentation. Quick question. The last slide of electrochemical stability was too fast for me. So it's not clear when you add the molybdenum oxide, the electrochemical and chemical stability in acidic, is that good or not?
I didn't get so.
Is the addition of molybdenum oxide, is that good? I mean, it doesn't sound like electrochemical stable in acidic medium. I'm surprised.
It's very stable in acidic medium. Really? It's leaching mainly in alkaline medium, but also in acidic, it's important to have it within the substitution site of titania rutile.
So this is the chemical stability, and the electrochemical stability. Can you go to high potential in acidic medium in molybdenum oxide?
I think I don't know. So I have to
will
check
be
it. Probably
surprised.
it's more easily oxidized to 6+ state when it is not incorporated into the lattice, and I guess that so it's electrocorrosion, I would say, and the leaching is due to this presence of molybdenum 6+.
I see. Thank you.
But I have to check it.
There are no other questions. Let's thank again the speaker.
Thank you.
Well, for the next 30 minutes, I invite Dr. Antonio Chaparro from the Department of Energy of CMAT company, Spain. Dr. Chaparro, thank you.
Thank you very much, and thank you, Michaela, for inviting me to this workshop. I'm very honored, and it's been 2 days with much Romanian culture and top science. So congratulations for it. And well, my talk is about the transport properties in electrodes from proton chain membrane fuel cells. The previous talk was about the catalysis, how the catalysts are made. So in my case, we are going to talk about the preparation of the electrode. So this is the summary. I will talk about the gas diffusion electrode of proton chain membrane fuel cells, and I will explain the problems with the transport, and I hope you will understand. I will be clear that this transport is a matter of the preparation of the electrode, so it's a principal issue in the transport properties. So I will explain through transport properties, through preparation methods, properties of the catalyst layers that are being obtained, mass transport resistance and impedance, and finally fuel cell response. Let me give you a brief introduction about the center where I come from. Is in Spain, is CIEMAT, which is the research center on energy in Spain. And we are placed in Madrid, in the center of Spain, but there are other centers of CIEMAT in other parts, for instance, in Almería, where there is a Plataforma Solar of Almería for solar thermal energy research, in Extremadura, in Soria, and in Barcelona. Our center has general facilities on material analysis, microelectronic workshop, superconducting, supercomputing, technology transfer, information. We make use of these facilities. In Madrid, we are the fuel cell unit. This is a picture of all of us. It's headed by Tomás González, and there are three groups: high temperature fuel cells by María Escudero. I run the low temperature fuel cell group, and the system integration by Tomás González. And our group is working in PEM fuel cells in 2002. And we are covering all different aspects of this technology. We are working on basic principle of the electrochemical reactions. We are also making electrodes, characterization, and preparing catalyst-coated membranes. We make also the analysis of these catalyst-coated membranes in single cells. We applied and are participating in normalization activity of the International Electrotechnical Commission. We also make small cells. We call them portable cells because you can run them on your hand. I'm not going to talk today about this, but it's a very important part also of our activity. We have 3 patents. One of them is already licensed by a Spanish company. And we put these cells also running in small applications. So for those of you that are not aware of the hydrogen fuel cell, the PEM fuel cell is an electrochemical device where with a cathode. In anode we have the hydrogen oxidation, the cathode the oxygen reduction. It is the most efficient way to convert hydrogen into electricity. It's a direct conversion. And the low temperature fuel cell are one special type of fuel cell, which is probably the most developed fuel cell type. This is a scheme of a low temperature fuel cell with the anode, and with the core size, the core of the cell is the membrane electrode assembly, which is the 2 electrodes on each side of a membrane. This is the cross-section image of a membrane electrode assembly, and in this, the electrodes are called gas diffusion electrodes. They are porous structures where you can see the three phases, the liquid, solid, and gas, are coexisting in closed space. So these are called 3-phase boundary. This is completely necessary for the fuel cell to run. And these phases makes the transport of liquid gases and electrons fast enough to produce power. The membrane, it has a high ionic conductivity and a low permeability to gases. The electrodes are composed of 3 layers: catalyst layer, microporous layer, gas diffusion layer. The catalyst layer is where the reaction takes place. Okay, and here again there are the 3 phases: the gas phase, which are filled by hydrogen or oxygen gases. The liquid phase is water filling partially the pores, and the solid phase, which is the pore walls, and where the catalyst is placed, the platinum, and the ionomer. So we arrive to the problem of transport. Transport when here we have the catalyst layer. Oxygen must transport towards the catalyst centers where liquid water is produced, and this water must exit the catalyst center. If it remains there, then you got a problem because the electrode becomes fluid. So this transport process must be fast enough. Once we are using platinum, which is the catalytic part of the reaction, is the transport the limiting process. Close to the catalyst, we have also a complex process which is being studied nowadays. It's not clear how it is, but the oxygen must somehow cross the ionomer film and enter into the catalyst particle. And here processes like surface diffusion are taking place. In this part is molecular diffusion, Knudsen diffusion, and water is principally by capillary transport and diffusion being transported. So as you can imagine, these transport processes are closely related to the porous morphology of the catalyst layer. And this morphology is a consequence of the preparation methods. So that's why I'm studying, we are working on this preparation method. Among different preparation methods, the ink deposition techniques are the most used, both at laboratory scale and also in industry. We can classify them into 3 types. The manual impregnation, which is just taking the drops of the ink and pouring them onto the substrate. The spray, which is a wide amount of techniques. They are spray coating, they can be also inkjet coating, different sprays. The property or the particularity of this spray is that it is a wet deposition process. So the ink arrives at the substrate with the solvent, so it is a wet deposition process. And the electrospray, which is the technique we are working on since almost 20 years ago, which is a process which is a dry deposition process with the part from an ink, which is a suspension of the particles and of the ionomer, but it is a dry depositing. These are different properties of the techniques. In red, I put the positive properties. So electrospray is our task, has the most red parts, but it depends also what you are interested. For instance, for industrial application, it is the spray. Many companies nowadays are asking how to make fuel cells, how to prepare, how to make a factory of fuel cells. We don't say them to use electrospray, but to use spray, because at the industrial level, it is nowadays it is more profitable. But for instance, in terms of reproducibility, the electrospray is higher. So in laboratory scale is a good way to study, to make a systematic study of catalyst. Also the efficiency into the substrate, we are depositing platinum, so the efficiency is very important, is higher on the electrospray. So this could make electrospray also of interest in future for industrial application. the performance, and I will show in particular due to these transport properties is also improved by electrospray method. This ink deposition is starting from the ink. The ink is a system, is what is called a polymer colloid system, where the particles and the catalyst particle, the ionomer can be dissolved, or can be adsorbed on the particles, or can be forming bundles, semi-solid bundles. So all of them are in these drops of the ink, which the characteristic depend much on pH, temperature, sonication, solvent property, the dielectric constant, the concentration, the aging also have influence of the ink characteristic. The ionomer, which I mentioned before, has a role on ink stability, but mainly has a role later on the catalyst layer as a binder for the particles, as a protoconductor, and in electrospray also it determines the hydrophilic, hydrophobic character of the catalyst layer. So this is our setup, particularly spray deposition with an airbrush, so you can see a dot, and you can see also that the part of the ink is outside the active area. So this is why we say this is not 100% efficient. Some platinum is lost. You can find commercial equipments where this can be improved, but in general is a problem of spray techniques. So this is how the spray takes place. The drops of the ink are atomized, and they are deposited in wet method. So you evaporate most of the solvent, some of the solvent in flight, but most of the solvent on the substrate. As a consequence, this is the initial spray film. You see this structure when you deposit it on Nafion membrane, which has this coffee ring characteristic, is quite inhomogeneous, and the distribution of the material depends on the substrate. Here is on indium tin oxide substrate, so and on the rheologic characteristic of the ink. Then you of course you grow a thicker film. You have a porous film which can work in a fuel cell. So now let's go to the electrospray method, which is by applying an electric field between the needle and the substrate. It is a method, or it is a process that was studied first in 1917. These photographs are quite similar to those we can obtain today, so it's a great work, experimental work. And this method is here briefly explained. We apply the electric field, so we charge the particles, and they are deposited in the presence of this large electric field, so in a particular way. It will make the morphology of the film to change, also the dendritic growth of the deposit. This is a film. Here you can see the electrospray. You cannot see the ink falling onto the substrate, because this is forming this cone shape, no? And you will not see nothing of platinum going outside the active area, because all the platinum is being attracted to the part which is electrified, which is the substrate where you want to deposit. Briefly, this process is an electrochemical process, so at least we are electrochemists, and we understand in this way. So you have the electrochemical reaction on the needle, you produce the charge, and these charges are adsorbed onto the solid particles, the ionomer and the platinum carbon, and when they arrive at the apex of the inverted cone, the Coulombic explosion, there is a large density of charge. It makes tiny homogeneous drops of the ink that arrive dry at the substrate due to the solvent deprivation by droplet fission in flight. I explained this a little bit. Here is a drop which is falling, and since the solvent is being evaporated, you attain a high density of charge beyond the limit of the stability limit, and then these drops are broken. All this is occurring at a fast rate in flight, so you get a fast removal of the solvent, and the particles, the platinum carbon and the ionomer is falling in right way on the substrate. These are the parameters we use normally for depositing with electrospray in composition, temperature, substrate, DC voltage, capillary diameter, substrate distance. All these parameters you can change, so you will change the morphology. We don't have, we do that by trial and error, so you will get always the same morphology if you use the same parameters. The mechanism of growth of the film is a matter of a complex simulation, mathematical simulation of this process. This is a catalyst-coated membrane. The membrane, you can bend it. The catalyst layer is properly fixed to the Nafion membrane, so you can operate. You cannot put your finger on top. You cannot make bad things, but that is, you can manage to work with it. This is the microscopic vision of this catalyst-coated membrane. Here you can see, you can notice this dendritic growth, which I mentioned before. And here we compare at the optical microscope. These are the coffee rings when you get spray. With electrospray, you don't have this. You have the particles homogeneously distributed from the beginning onto the Nafion or wherever the substrate. These are now properties of this catalyst layer, the porosity. The porosity we see here, this is electrospray at 2 Nafion concentration. The concentration on Nafion will make a change on the porosity. You can see here, this 15% concentration, we have larger porosity, macro porosity, which has a role in the water transport mechanism. Here it is compared with the commercial layer. You can see these cracks that normally appear on commercial layer, or layer prepared by airbrush. There is no crack in our electrospray film. You notice the difference in the scale. So this is a property of electrospray layer. Due to this layer porosity, we have thicker films. This is one issue where this cross-section can show you, well, it is a little bit deformed due to the cutting of this particular sample, but you can see the porosity in this layer, which are macroporous, and you can compare at the same magnification with a commercial catalyst layer. And another I don't know what happened. Okay, another property, very important property for liquid water transport, is the superhydrophobic character, and you can note you can see here the this dendritic growth. This makes this Casey-Baxter model for superhydrophobicity, so pockets of air. So you have a very hydrophilic material, which is the ionomer, but you are making a superhydrophobic surface or porous surface out of this very hydrophilic material. It's a contradiction, is seen in another superhydrophobic surface, but it makes a difference for liquid water transport in the fuel cell, as you can imagine. These are measures of the catalyst layer mass transport resistance. Is measured with hydrogen limiting current at the National Laboratory of Berkeley by Adam Weber group. And we see that the catalyst layer prepared by electrospray do not show the typical increase in mass transport resistance when we go to very low platinum loading, which is being a problem to decrease, one of the problems to decrease the amount of platinum in these fuel cells. If we go back to the transport processes, we think that these transport properties are improved by the electrosprite field. This is the scheme of what we think is the situation within the cathode. The water is not longer forming a layer of liquid water on top of the particle, but they are tiny drops of water. So oxygen has more facilities to attain the surface of the particles and to make the reaction there. Well, another method that we are using this is just a brief explanation of this mass transport resistance that we are now working on, is a technique where we make the impedance, current modulated hydrogen field rate spectroscopy, the impedance of the flow rate of hydrogen, which we measure at the entrance of the fuel cell with the current. Okay, so if you make the quotient, you get a mass transport impedance. Here the concept is explained. We modulate the current, so we modulate the transport of hydrogen, and we get this kind of spectra in Nyquist plot where you can see different processes occurring in different places of the distance from the anode. From the anode catalyst layer towards where the flow meter is placed. Among this process, as you can imagine, is the catalyst layer. We have made this. First, the apex or the maximum of the imaginary part is related with the diffusivity in this area, in the place where this process is located. So we are changing from commercial to the electrospray catalyst layer in the anode, and we see a difference in we see that the absorption of the modulation is lower in the catalyst layer prepared by electrospray. The absorption is more or less related with the length of this vector. So you see here that the better transport properties give rise to the lower absorption of this modulation. And finally, to show you just the polarization curve with two catalyst layers, in this case in the cathode, and you see an improvement in the resistance of the cell. The internal resistance of the cell at zero frequency is related with transport properties, so this is the improvement, and also the diffusion limited current is also improved by this electrospray catalyst layer. We normally have about 20-25% improvement in the peak power density of the cell. So thank you very much for your attention. These are the persons that have participated in this year with me in the work, and also thank to Adam Weber for the mass transport mission. Thank you very much for your attention.
Thank you for the presentation. Can you come back to the slide that Adam was making the measurements of the resistance? So you stop, unfortunately, I see at, what is that, 0.002, like 20 microgram per platinum per square centimeter?
0.1, 0.2, 0.3.
Yeah, do you have any data even lower? That's very interesting.
We have data on polarization curves, and the cell is no longer working properly.
Oh.
Below this loading.
Oh.
The cell, the efficiency of the cell is not high.
Okay.
These are mass transport properties, but it's not polarization curves.
Okay. Anyway, so one quick comment regarding, there are some people, also myself, working on electrospinning of ionomeric material. So when we add some nanoparticles, like a catalyst, there are some properties during the electrospinning, the catalyst go out to the surface of the nanofiber. So then the catalyst is not covered by the ionomer. So that is maybe the reason I might guesstimate why the oxygen transport is so fast and then the resistance is so low, because the catalyst is on the surface. You are actually not doing electrospinning, but the same process, and you have ionomeric and catalyst. So I think that you will be able to see something like that in TM maybe, or
some of the
so the catalyst, you may be able to do some nanofibers of the naphthalene,
but this is an electrospinning.
And which is similar actually. This is
but
more or less what you're doing.
We don't have nanofibers here.
I know, but this is the same process. So maybe I say that the catalyst go to the surface, to the ionomeric material, whatever the morphology is. Maybe.
But the surface of the ionomeric material is very difficult to be observed, even in transmission. We don't know really where is the ionomer. It is perfectly joined to the catalyst because we made the compositional analysis.
Yeah, I know.
But we don't know if it is on the surface or
no.
Thank you.
Thank you.
To what extent can the mass transport limitations be improved by multiple level hierarchical pores, as some other people have discussed in this meeting in other contexts? Do you think that could be designed into either of the electrodes?
Hierarchical pores, yes.
Yeah.
Of course, capillary transport of the liquid. This would benefit from this hierarchical porosity of the. There are some works on doing the catalyst layer on this way.
Yeah.
It is a more complex way to make the catalyst layer. You have to take into account the industrial application also, but of course it would be it is an improvement in the water transport.
Thank you.
Other questions? Okay.
Thank you for the very informative talk. I have actually two questions. So one is regarding the electrode spraying. Is there any requirement for how you prepare the ink? And there has to be like special substrates. And like, can you maybe deposit on carbon fiber mats instead of naphthalene? And the other question is, why do you think it's not industrial applicable? Is it because of the restriction on that you can't deposit on larger areas?
Okay. Well, regarding the first question, is the substrate. The substrate has to have some conductivity. It's electrical conductivity. For instance, naphthalene, which is a plastic, the conductivity of naphthalene, the protonic conductivity in air, is enough to to have the electrospray deposition. So it's a small conductivity. You cannot deposit on Teflon, for instance, because it is not conducting. No? And about the industrial application, the biggest problem is the rate, the deposition rate. We need a few hours to make a 15 square centimeter electrode. So this makes this system too slow for industrial application. Although there are possibilities to improve these rates. This is something we are also working on. Thank you very much.
Thank you.
Okay, if there are no other questions, let's thank again the speaker. And now I have the pleasure to invite the next speaker, Dr. Dario Dekel from Israel Institute of Technology, Israel. 2 minutes.
Hey, that's not my presentation, but I assume that you can help me. So thanks very much for the introduction. Michael is not here, so I would like to thank Michael and all the organizers for the invitation. It's my first time in Romania, so I'm really excited. And this is an excellent organization, an excellent speaker. So far, until now, all speakers were good. So really happy to be here. So I came from Israel. We are a very, very, very tiny country. So the only way you can see us in the map is to show at the night. So you can see the size. So we are actually Romania, which is not a huge country, I must say, is 11 times bigger than Israel. So we are indeed very tiny. Wherever you are in Israel, you drive 30 minutes, you are already outside of Israel. So that's more or less. So we are in the north, still we have north in Israel. So Technion is in the north, one of the few universities. Is ranked around 80 in the world. So for a tiny country, again, this is not quite remarkable, I would say. It was founded 100 years ago, even older than the state of Israel. So at the Technion, I joined the Technion eight years, more or less, ago. So we do all what we need to do in order to develop the anion exchange membrane, fuel cell, water electrolyzers, and different electrochemical devices. So again, we do not just deal with fundamental studies and development of polymers and membranes and functionalized membranes, but we also develop catalysts, mainly for fuel cells, ORR, HOR, also for electrolyzers, AM electrolyzers, so HER and OER. We do the test of the materials, characterization, develop. We do numerical modeling to try to understand this technology and therefore to develop better materials, all the way to single cells. And this is my hobby. So we aim to be the next generation of fuel cells for this automotive transportation. Of course, we're not alone. Every time I say we, actually, it's a growing community. We have communication and collaboration with many, many of the leaders in this technology. So in this way, we make a fast progress. For those who are not familiar with that, so just very quickly, an ion exchange membrane is like a proton exchange membranes, but we conduct hydroxide. So we have quaternarium ammonium, for instance, instead of sulfonic acid. We functionalize the polymer, and then we conduct the hydroxide or any other anion. We have different ways to functionalize the polymers. There are many advantages and disadvantages, but in principle, this is what we want to do to conduct the hydroxide. So we'll talk today about fuel cells, but we work with water electrolyzers, and there are many uses that we have already in an ion exchange membranes, like artificial muscles, energy storage, redox flow batteries. We have also fuel production, CO2 reductions, CO2 pumping, and very interesting new application that we do in our lab. So it's very useful to work with this kind of materials. So just for instance, an ion exchange membrane water electrolyzer, just a couple of advertising of our latest reviews. This is with our colleagues in Europe, all what you wanted to know about an ion exchange membrane water electrolyzer, which is very, very young technology. And also this one that many countries were on this actually huge review for all water electrolysis, just PEM and including alkaline with KOH and an ion exchange membrane water electrolyzers. Believe that that became the kind of handbook for this technology, which is actually a very hot topic, mainly here in Europe and also in Korea and Japan. Now coming back to fuel cells, but all what I said about fuel cells is the same for water electrolysis based on an ion exchange membrane. So what we do is we take, for instance, proton exchange membrane fuel cell, we take the advantage of the solid polymer electrolyte, and we just change this membrane and we conduct hydroxide, as my colleagues used to say, in the wrong direction. But in any case, what we want to do is to have an alkaline medium instead of very acidic medium. So then the electrochemical reactions are in alkaline difference, are more favorable, so we can kind of facilitate the removal of platinum or all precious metal actually that we can do. So that's the final goal. If you remove the platinum, and we use iron, nickel, cobalt, and even carbon, I will show one slide on that. And of course, because it's not extremely acidic, we work on alkaline medium, so we can use hydrocarbon membranes that are significantly lower cost than fluorinated, and also have many advantages. And then, and this is based on 500,000 of fuel cell stacks for automotive per year. So you can see we aim to have a 50% cost reduction. Same happened more or less with an ion exchange membrane water electrolyzers. So you can see that technologies are really very young. When I started that around here 15 years ago, co-founded a startup company. It was the first actually mover to this technology. There were only 3 groups, 3 people around the world working on that. Since then, you can see the topic is very hot. We're moving and have more groups around the world. Most of the papers come from the States and from China. Israel is here. However, if you, for a tiny country, if you divide by the number of population, so we actually are the first contributor to this technology. So you can see very quickly, since we started here, I was working with a milliwatts level. And you cannot power at that time even your cell phone. Today we are talking about amps per square centimeters and watts per square centimeter. So incredible fast, rapid progress. And the main reason, one of the main reasons for this fast progress, the same happened with the even younger technology for an ion exchange membrane water electrolyzer. And the main reason is the fast progress that we as a community made to develop this kind of an ion exchange membrane. So at the very beginning, we were talking about 10 millisiemens per centimeter. I still remember all my colleagues coming from PEM, from Nafion, of course, telling me that that will never be work, this idea, because we will never be able to conduct hydroxide as fast as we conduct protons much smaller. And today you can see, and actually a few years ago, you can see numbers like 100 millisiemens per centimeter, which is Nafion more or less, and even higher. So this is already proof that indeed you can in polymer and solid polymers to conduct hydroxide very fast somehow. So in terms of catalyst, we started saying and noticing that this is extremely difficult in the anode for the cathode. We'll talk about that later, but we have many options for alkaline. However, we saw and we understood that there is a real challenge in for the hydrogen oxidation reaction, which in acidic, nobody look at that. Probably you never heard the presentation about the HOR in acidic, because the kinetics are so fast that nobody cares about that. You put 1 nanograms of platinum and you can get very high power. However, and then this was the first review that we made on this topic, and we explain actually that we show all what has been done in the literature, and we show that we have 2 or even 3 orders of magnitude lower kinetics in the HOR in alkaline as compared to acidic medium. There are many reasons, and there is no consensus of why that happened, so we bring in this review all the reasons that were published. However, I like to, in very simplistic way, I would say, to mention the 2 following things. If you compare, you have the triple phase boundary here, you have the electrolyte, the carbon support, and the catalyst. If you look at the acidic, it's a very simple reaction, actually. You oxidize that, you remove the proton, that's it, you go home. In the alkaline, you can see we have 2 reactants, not just 1. That means that besides bringing the hydrogen to the surface of the catalyst, you also need to bring 2 huge anions to the same position. So this is really, and that coming not from the air, from the voice, coming from the electrolyte. So it's really challenging to do that. This is one reason. Second reason, you can see here, you do not have water. Here in alkaline, we have water as a product, and we have a lot of water. We have 2 water molecules per couple of electrons, meaning that once you succeed finally to bring those 2 species to the surface and oxidize the hydrogen, you have water around the catalyst. So you add that additional resistance for the hydrogen to penetrate to the site of the catalyst. And if you do not remove quickly this water, so we have more and more water, not to talk about flooding of the electrode, that's another issue. So those 2 simple things are showing or indicating that this should be a much more problematic reaction. So we don't have much time, so I will go all the history completely to the final catalyst that we are working with in the past 3 years. We developed several successful catalysts before that, but all based on platinum, platinum Syria, platinum nickel, etc. And now we finally, a few years ago, we succeed to make these nickel iron, some special nickel iron nanoparticles that actually we succeed to have a, let me say, reasonable reaction, reasonable activity in alkaline. Still not enough. You can see the power is really low. It's a 60 milliwatt per square centimeter. The good news is that this is the first, not just PGM, but critical raw materials catalyst for the anode for this technology. That maybe is the second one. There are just a few publications that succeed to do that, so we were very happy with this, even when the power is not significant. And this is, again, completely PGM-free, completely CRM-free, actually, one of the first in the literature. Now, the past year, 1 year ago, we succeed to have this, or kind of modified nickel iron. Actually, that nickel iron, always, all nickel have a kind of nickel oxide, natural coating, let's say, around the nanoparticles. So we, for the first time, we were working for this for years, and we succeed to in situ reduce this oxide level inside the cell. So when we operate the cell, we do kind of, we call it activation, let's say in that way, that after a few minutes, we succeed to do, this is ex situ, so you can see here the active after, before and after the activation, so the nickel is now reduced the oxide level, so it's significantly more active than in the HOR in alkaline. In the fuel cell level, we also do the same activation, so we come from a really poor open circuit voltage to 1 open circuit voltage, meaning that we succeed to reduce most of the oxide. And then you can see here, actually you cannot see, but in red here it's almost 0, the power of the fuel cell using before activation and after activation. This is the highest ever power density that we could succeed, everyone could succeed to get from a PGM or CRM-free catalyst in the anode. You can see here there were only 3 papers, 3 groups that succeed to do that. We are here now close to publication. So we are very happy with this activation method that opens actually the door to many, many other nickel or nickel-based catalysts for this technology. Now, doing completely PGM-free or CRMF-free, so now we succeed to triple the power density, so we are not anymore in 2 digits, we are in 3 digits, so you can see also this is quite a record, so we are again happy that these results will be published very soon. Now here we develop a numerical model, so with the numerical model we can also are able to see, evaluate the different contribution of different components, including the electrodes. So we can see here the HOR over potential, and we can see also the ORR potential. So this is significantly higher also than HOR. So we also need to keep working on the ORR. Now the technique we're not expert in electrocatalysts. There are many experts in the world, so we collaborate with anyone. Most of them work with PGM or PGM-free, some of them even with CRM-free. So we decided at Technion try to do something that nobody or most of the people do not do. So we went all the way to the cheapest catalyst we can think about that. So we have metal-free catalyst, and we decided to go to the most dirty catalyst that I know. This is just graphite. You can buy in tons for a few dollars. Every time I ask for a few grams, so they ask me, the companies, which type of container I need to ship you that, so that we need just a few grams. Really, really very cheap. So we decided to use that graphite as a raw material, so it's completely metal-free. And we decided to do also to the most cheapest and simple process or room temperature using ball milling. You can have that at your kitchen, and this is a few hours. We can have 100 grams with no cost at all. So sometimes we put, of course, some salts, also very low cost, and then we just dope the graphite with some different heteroatoms. And we hope that that will work, but that worked actually extremely well. You can see here, this is the mill graphite. And then when we dope with different heteroatoms, so we can increase the, that's the ex situ results. In some cases, like doping with nitrogen-based salts, we can have a 150 millivolts increasing in activity, which is extraordinary well. So we went all the way to fuel cells. You can see here, most of the cases, some of them relatively good, but some of them extremely good, so more than 300 milliwatt per square centimeter. This is just the first shots of no optimization at all, not in the process, not in the type of heteroatoms and the amount of doping, and not in the fuel cell, so this is very encouraging. Also the type of stability that we show, because we do not have any metal, so all the degradation mechanism involving metal dissolutions and growing, etc., is not relevant here. Probably we will find others, but so far this is very stable in most of the heteroatoms that we use for doping. Now, we have a unique opportunity at the Technion that we work with polymers, we work with electrocatalysts, so we can work on the interaction. That this is very rare because most of people in the community, if you are a polymer chemist, you develop membranes, but you do not deal with catalysts. If you develop electrocatalysts, you're expert in that, you do not deal with ionomeric materials. So we work on the interaction, which is extremely rare to find some publication on that, and this is extremely important as well. So this is just, I will show some very quick examples of what we do. So this is a collaboration with Yusen Kim from Los Alamos National Labs, and showing that the different, when you have a PGM, different functional groups that we use, so that functional groups can be deposited or absorbed on the surface of the catalyst at certain potentials, and that will be changing the electrochemical activity of the catalyst at the beginning of the activity. So this is very important. I was the first ever paper actually showing that, and my colleague keep working on that, showing extraordinary new data. This is another example. For instance, we try with my colleagues in University of Montpellier that showing that if you have different catalysts and different ionomers, if you test ex situ your electrocatalyst, in RDE for instance, depending of which type of ionomeric material you use, you can get extraordinary differences between the activities. And the only reason, as per our hypothesis, was that the different ionomeric materials have a different permeation of oxygen and hydrogen, and therefore have different access, and that affect the electrochemical activity of the electrocatalyst. So in terms of when you are in PEM fuel cell, that we have membrane, nothing ionomer, so we don't deal with that. In this technology, we have the flexibility to have a wide range of materials. However, we need to take care about these interactions that are critical, even if you work on membranes or even if you work with electrocatalysts. Another example is we learned from our numerical modeling that actually the water contents in the electrodes are completely different. This is not the case in PEM fuel cell. We have, of course, some differences, but here we have a very, very high content of water in the anode, and this is reasonable because we generate a lot of water in the anode, that in PEM we don't have it. And in the cathode, we have extraordinarily low amount of water, and this is because the water is a reactant for the ORR in alkaline. Again, the water is not reactant in PEM fuels and in acidic medium, so that's something new, unique to this technology. And for that reason, we have a huge gradient here, which is very challenging, I would say, for the cell, for sure for the membranes, but also for the catalyst. So we have so low content that actually you do not have enough water to solvate the OH minus. So the OH minus is microsolvated, and then the structure and the reactivity of the OH minus significantly different. So we took a couple of years and we developed an ex situ method, and here we measure the functional group that are part of the anion exchange membrane. And we measure how these cations, how this functional group degrades during time when we have different water content. So this is a lot of water and less water, less water. We found that the reactivity or the degradation kinetics have 2 orders of magnitude higher when you have lower and lower water. And that affects, of course, not just the ionomeric material, but also the electrocatalyst. Because once you do not have reactivity, so now we put all that degradation data inside our model, and we can see what happened inside the model. So the model says that during time, we have degradation of conductivity of the ionomeric materials here in the cathode ionomer catalyst layer and in the membrane, but not in the anode. Meaning that if you choose the wrong functional group and you have certain temperature, certain current density, operating conditions of your cell, you actually can have no whatsoever effect onto the electrocatalyst of the anode. However, you destroy the electrocatalytic activity in the cathode because you don't have enough water, because you don't have enough conductivity of the OH minus. And then we found that using the same numerical modeling, that if we have a membrane that's nothing to do with electrocatalyst in principle, but we have a different diffusivity, water diffusivity of the membrane, we can have a completely different water management. So if you have a high water diffusivity, you have a long life of the cell. If you have a low, you have a low life of the cell. And this is because if we have a lot of water here, water diffusivity is high, so we can supply that water, and then the cathode is happy and the electrocatalyst is happy, but otherwise you suffer and you reduce the voltage and have degradation. So that was one way actually that you say if you develop a membrane with a certain properties, you can have a better catalyst or better catalytic activity in your cathode. So it's very related even if they do not touch each other in principle. So coming back to the low water, if you have low water, we also found that again, the reactivity of the OH minus, again, different cations is much more severe. And then you lose the cation, you lose the OH minus properties. And we found that all the different cations that we use and all people using this technology, all of them can be degraded and all of them will be degraded much faster if you have lower amount of water. So this is an intrinsic problem that we need to develop better functional groups for this technology that are more stable in low hydration content. So the technique, we developed a few functional groups for these technologies. This is the last one that we developed and recently patented. So this is a family of isoindolinium, not completely different from what we know, but this is very, very stable at low hydration numbers. I must admit we do not know in advance. We cannot understand yet which functional group will be stable in low hydration numbers. So it's unfortunately trial and error. But successfully, we have some good results so far. Now, using those functional groups, so we can now go to much higher temperature because the functional group is not degrading. And then we could increase the conductivity. For instance, here, one of our membranes we tested have at a relatively low temperature, more than 100 millisiemens, and we went all the way to 80 and even to 120 degrees Celsius. So this is the first time that we could go to very high temperature, even above 100 degrees Celsius. As you can see, not more laser, you can see the high conductivity of 300 millisiemens per centimeter. This is so far the highest conductivity, hydroxide conductivity ever measured for an ion exchange membrane. So this is thanks, of course, to the membrane, but also to the higher temperature. And therefore, we went all the way to fuel cells, getting a very high performance, of course, because this is high temperature. But also, we can go back to catalysts, that PGM-free catalysts that were not so successful at low temperature. But then more than 100 degrees Celsius, you can see we can get more than 1 watt per square centimeter thanks to this higher activity at higher temperature due to the high stable ionomeric material. So another way to relate the work that we do on membranes and ionomeric materials to electrocatalysts. So this is a new field we call high temperature anion exchange membrane. And we are working on that nowadays, so we hope that we will get new results. Now, the last two slides, we also found very recently, I mean, until 3 years ago, I was always asked about the radicals in alkaline, in fuel cells. We know that this is a huge issue in Nafion and in acidic environment. We have no reason to believe that there are no radicals, but I always need to do like that and say, I don't know. Nobody knew about that. So a few years ago, we started working finally on this. And we performed the first ever in situ, EPR in situ test on the fuel cell. So we were operating an ion exchange membrane fuel cell and we measured the different radicals. So we have several inputs. First of all, we measure radicals in the high amount. So we could answer, today we can answer the question that there are radicals in situ in alkaline fuel cells. The second that was very surprising, we have radicals we measure in both cathode and also in the anode. Different species, but this is very, very interesting, unexpected, I would say. We are now working how those radicals affect the polymers. And of course, we have initial results. One colleague of mine also published a first paper on that, saying that here is the degradation of the functional group due to this radical that you found in the fuel cell. So we are working on that. And of course, we notice that also have some degradation in the functional group. Not also in the functional group, also, of course, in the backbone of the polymer, similar as we have in the acidic medium. So this opens, again, a new field that we will need now to develop membranes, an ion exchange membrane that are stable against the radicals. And we are working with a group in collaborating in Cornell on several ideas how to add scavengers, radical scavenger inside the catalyst to try also to absorb those radicals before they go to the membrane. So last, I need to thank a long list of collaborators. This is really a very partial list. This is, again, some picture outside of the campus in our city. That you look from the Baha'i temple, Baha'i garden, the temple, you see the German colony somewhere here, and the port in the north of Israel there. Very nice city, very beautiful view. So you are all invited to visit. Special thanks, of course, to all my group. This is an old picture 1 year ago, but there are no integrants, a very diverse group, really very smart guys. They do all the job. I just talk. And I need also to say thank you to many funding sources, and thank you for the attention. Thank you very much.
Questions?
Okay, thank you. Thank you very much for this impressive results on fuel cell, alkaline fuel cells. I have two questions. One of them is if carbon dioxide, environmental carbon dioxide is an issue for these alkaline fuel cells, as it used to be with the first alkaline fuel cells of the 1970s.
Yeah, we need to make to differentiate between alkaline, what I call conventional alkaline fuel cell that have KOH, liquid KOH, and an ion exchange membrane fuel cell. So although the name is longer, I say an ion exchange membrane fuel cell, we don't have liquid KOH. So the short answer is no, there is no issue, but I have a longer answer as well that we need to treat that. In principle, the way I call it an ion exchange membrane and not hydroxide exchange membrane, as my Chinese colleague they used to call it, is because when we have CO2, the CO2 dissolving water react with the OH minus that we generate at the cathode. So we have bicarbonate, carbonate, and hydroxide. All three species go into, so I call an ion exchange membrane. You transport all the species. There are some advantages and disadvantages. That's even longer answer. But in principle, those carbonate species, you convert back to CO2 and you move back through the anode, you remove that. But there is some engineering challenging there. But the short answer is no.
Second question is this, since the anode and the cathode have different water contents, have you tried changing the hydrophility, doing anode and cathode with different hydrophility in order to conduct the water through the membrane towards the place you...
That's extremely difficult, and this is one of the challenges. This is a beautiful challenge because we have a lot of things to do and we can manage that. Now, one of the actually advantages of working with hydrocarbon backbones is that the permeability of hydrogen is extremely low, normally 1 order of magnitude lower than the naphthalene. That allows us to make a much thinner membranes. So for instance, we can work with 10 micron membranes, which naphthalene, you cannot do that, to say that gently. And we can go even a little more thinner. And mechanically speaking, this is very robust. We're working with polyethylene membranes, so this is very robust mechanically speaking. So when you have a very thin membranes and we're working now on high water diffusivity, so we use all the water that we have in the anode to work in the cathode. So actually we are reducing this gradient, but it took us a few years to understand how to do that, yeah.
When we speak about catalyst stability, you have a timeline of 0. several hours, and when you switch to membrane stability, you talk about 100 of hours. Why this gap?
Because, the Israelis are very impatient, so I need to cut things and say, okay, move on. So we really tested just a few hours. Both membranes actually and catalyst, we have enough experience to understand if that will be stable or not. In some cases that there were no data, like in case of membrane and stability, that I show more than even 1,000 hours. So nobody, and they have intuition, but no real knowledge. So we actually tested that for a long period of time to try to understand where we are going to do. Yeah, today we have much more experience. We developed a new method, for instance, for testing catalyst and membrane stability ex situ. And we can see a very linear, in all cases, all the materials, a very linear forever degradation slope. So then if we tested, let's say, a few hours or even 10, 24 hours, so that's enough to get some idea of what is going on. Yeah, but that's a good point.
I had a couple of general questions. So you mentioned the 50% cost reduction, changing the catalyst to get rid of the platinum. I think we heard earlier in the week about the target of $1 per kilogram of hydrogen. How close does that get you to that goal? And then we're talking about degradation of radicals. Is that a limitation towards, what is your chief limitation once you get past the platinum?
Yeah, so first of all, that study, the cost study, we took the similar study from the US DOE, and we make the same assumptions and just exchange the materials. That it took 1 year to make that around 50%. I cannot say exactly, but this is a very good goal. And that's including also not just membranes and catalysts, but also the bipolar plates. We have some advantage because of the alkaline medium to make cheaper bipolar plate using stainless steel. How that relates in terms of, let's say, electrolyzer, how that helps us to go to $1 per kilogram. So I don't have the relationship. I also work on the cost of the bill of material, the cost of the stack, both fuel cell and electrolyzer. So it will bring us closer. I don't know if that will be enough to bring the hydrogen to $1 per kilogram, but it will be bring us significantly closer to that goal.
And is the degradation the next issue? For getting rid of the platinum?
So the degradation so far, this is the main issue that, of course, if you go to PEM fuel cell, and this is the reason why Toyota or GM, they of course, they keep working on PEM fuel cell. Also, it's very much mature, but they didn't came to the technology and invest yet in the technology because of this parameter. I mean, I work with the guys from GM every year, and they are very updated. There were a few gaps until 3 years ago, let's say, that we were closing. CO2 was one of them. And the only remaining one, which is actually the harder to overcome, is the stability. Mainly due to the stability, I was talking just shortly of the membrane. So this is what we're working with. So there's still a long way to go.
Thank you.
So still, I would like to stay at the CO2 issue. My question is the CO2 pumping you mentioned in the beginning of your talk can be an energetically more favorable process than the present technologies that used for removal of CO2 from air. So can it be used as an accumulation of CO2, and in this case, contribution to the CO2 technologies?
Yes, the short answer is yes. The complete and sad answer from my point of view, I was working on that. One of my colleagues, much smarter than me in Delaware, so he patented the idea and went faster than me, and he's working on that today. One of a startup company in Israel licensed this patent and is working on that. So this is extremely energetically favorable for CO2 capture. You know, you can do like we have in RO, in water treatment, those modules that you have 1,000 square meters of membrane, you can do like that and absorb CO2. And actually what you do not absorb, you just transport the CO2 using the properties. I mean, take advantage that this quaternarium ammonium will absorb CO2. You work with a very low current. Otherwise, if you have high current, you reduce the oxygen to OH minus, and you don't want that in this type of electrochemical device. So with a very small current, you transport the CO2 as carbonate species and concentrate the CO2 on the other side. So we are working now on other similar technology that I cannot present that right now, but using the same disadvantages of the membrane to make actually something good for me. Yeah. It's a very interesting idea, so my colleagues are working on that.
Thanks to Dr. Deckel once again. And I will welcome Nicoleta Ciotera, Dr. Nicoleta Ciotera from University of Craiova, Romania.
Thank you. I will raise the temperature for from 100 to 1000 degrees C now, because I will refer to several applications, among them solid oxide fuel cells and electrocatalyzed have an important role in increasing reaction rates, and among the process of interest are energy generation in hydrogen fuel cells, and not only hydrogen production through water electrolysis and CO2 conversion to create another fuels. And our goal was to establish the relation between catalyst properties and their activity, selectivity, and stability, with the aim to design new materials with improved properties. One of the main goals of sustainable development is to develop clean and affordable power sources. Solid oxide fuel cells are clean power sources, but until now not so affordable. So they still operate at quite high temperatures, about 1000 degrees C. And until now, the state-of-the-art anode materials is the Cermet nickel yttria stabilized zirconia. The drawbacks are well known: coarsening, sulfur poisoning, and carbon deposits growth. But alternative materials have been also developed without successful development in on the large scale. There are more challenges as in this type of fuel cells due to their quite high operating temperature, and the goal of researchers in this field is to decrease the operation temperature down to 600, 800 degrees C, the intermediate temperature range. We start our research 15 years ago with Syria, a quite simple structure material, and by doping and co-doping Syria, we managed to obtain materials with quite good conductivities in the intermediate temperature region. However, the lack of stability under reducing atmosphere was our concern, and in order to respond to this challenge, we switched to more flexible structure, to pyrochlor materials, pyrochlor titanium materials. We have in this case 2 cationic sites, and we can play with composition. There is more room to play with chemical substitution in order to to increase the stability and the conductivity of these compounds. And during our research, we discover a secondary phase, the lanthanum titanate with cuspidine structure, and we found it interesting enough to perform more in-depth analysis of this material, and we found in the literature the data of Slater and co-workers and Sedeno and co-workers, and 2 types of defects can be found in this type of materials: an oxide ion interstitial position and an oxygen vacancy position. And these 2 types of defects lead to 2 different migration paths for ions in these materials. Vacancy hopping migration path with an activation energy of 1.51 electron volt, and another migration path via interstitial oxygen with an activation energy of 0.49. That's why we try to substitute titanium with vanadium, as they have a very close ionic size, and we succeed this for substitution of 5% titanium with vanadium. We obtain a solid solution. So we have here also the lattice parameters and the lattice volume, unit cell volume for our samples. And what we do was to sinter the material and to evaluate the conductivity of the pure samples with temperature, and an increase in conductivity was obtained for the sample with 5% vanadium doping titanium side. And also we notice a slight decrease in activation energy. Our colleagues from École Nationale Supérieure de Chimie de Lille performed some calculation regarding the crystalline structure, and they have quite good results. They proved that vanadium substitute titanium in the lattice. We further in fact, the value of conductivity doesn't allow us to use this material as anode material, but we try to substitute yttria stabilized zirconia. We prepare composite powders with different content of nickel oxide by the same procedure, using a sol gel procedure, and we prepare symmetrical cells. We have a quite good distribution of nickel in the material. We intend to use this type of materials with Syria electrolyte, based electrolyte, but the reactivity test doesn't lead to the formation of secondary phases. Therefore, we perform the reactivity test with yttria stabilized zirconia, and we use this material as electrolyte because the reactivity, the X-ray diffraction performed on the mixture of the two materials, our composite and yttria stabilized, commercial yttria stabilized zirconia, evidence no secondary phases in the mixture after heating for 100 hours at 1000 degrees C. Therefore, we run some AES measurements at different temperature under hydrogen. And the results indicated a decrease in resistance with the increase in temperature. We also prepared a fuel cell. It's our first fuel cell. We use our materials with 20% nickel oxide as anode. We use yttria stabilized zirconia as electrolyte, and one material prepared at Institute of Physical Chemistry, Ilie Murgulescu from Bucharest, as a cathode material. We fed the cell with hydrogen, pure hydrogen at 700 degrees C. You have here an image of a cross-section of the cell. If we monitor the sample, the cell for 96 hours, after 24 hours we notice an increase in resistance, and when we remove the cell, in fact, we notice a complete delamination of the anode. We have a lot to do in this area because due to nickel oxide reduction and to the thermal expansion mismatch between electrode and the anode. We think that this problem can be overcome by using graded anode. So we still have a lot to work in this area of cell manufacture in order to have good results. In the past 2 years, we in the Department of Chemistry from University of Craiova, from where I come, we have also switch the interest towards electrochemical cells, because I have colleagues which are involved in the catalysis research field, and until now they are working on single metal oxides. They are playing a lot with titania-based materials, and quite recently we developed a collaboration with Professor Cârja from Technical University from Iași, and we tested layer double hydroxides and also mixed metal oxides coming from LDH. And we do this because we want to overcome the drawbacks of the single component metal oxide, and we want to have higher photocatalytic activity in our working electrodes. We perform characterization of the materials using XRD and Raman spectroscopy, and for LH we have the characteristic peaks of this type of layered structure, and also the peaks of cerium and iron, because during the synthesis procedure we intercalated this type of cations in the structure of LDH. And we perform photoelectrochemical characterization of the materials. We gain an N-type semiconductor behavior for all the investigated materials, zinc aluminum and magnesium aluminum LDH modified with iron and cerium, and also on their heat-treated counterparts. And we also perform measurements at Mott Schottky plots, from which we evaluated the flat band potential for all the samples, and from the electrochemical measurements we can conclude that the sample based on zinc aluminum LDH treated at 850 degrees C show a increase with 68% of photoactivity under illumination compared to dark condition, and both the LDH and the heat-treated sample have suitable potentials for water reduction. We have here the energy diagrams obtained from electrochemical measurements, and we can say that the investigated materials can perform water oxidation, and also the LDH and mixed metal oxides materials could be efficient in advanced oxidation reaction of organic pollutants. We also perform electrochemical impedance spectroscopy measurements for all the investigated materials, both in dark and under illumination. We have here Nyquist plots and Bode plot, and we found that the lifetime of photoelectrode increased under illumination, facilitating electron transport at the electrolyte interface. And we also found that the LDH materials based on zinc aluminum has the smallest Schottky slope, which is proof of highest carrier density. In conclusion, there is enough space to growth in electrochemical cells development, and the material scientist can have a significant contribution. Electrochemical methods are powerful tools for the evaluation of materials performance, and this work was elaborated by collaboration with École Nationale Supérieure de Chimie de Lille, Technical University Gheorghe from Iași, and Institute of Physical Chemistry Ilie Murgulescu. Thank you for your attention.
Okay. Just curious, what other types of characterization techniques did you use?
I use Raman spectroscopy combined with XRD because we are preparing nanocrystalline materials, and in order to evidence the crystalline phases in these materials, Raman spectroscopy is a powerful tool, more powerful than XRD in this case. We use SEM ADS analysis in order to evaluate the composition and the morphology of both powders and sintered materials, and that's all.
Okay, thank you.
You showed the plot, the famous plot for electrochemistry, where you showed which materials span the oxidation and reduction potentials, right?
Yes.
But I always wonder, if we have a nice material, but it's too low or too high, can we just add a dipole layer at the surface to shift the potential, or will this not work?
I don't think it's enough just at the interface, at the surface of the
At the
electrode.
interface, which would
At the
change the alignment to vacuum, yeah, you see? So the material would have the same gap, but it can be shifted up and down. Maybe I'm wrong, but I think this should be possible. Okay, we can talk about it more later.
I don't. We work under a liquid water. In this case, we work with diluted natrium sulfate.
Sure.
As electrolyte.
No, I mean, take a.
I don't know what you mean by vacuum, or I didn't understand well.
If you have a layer that has a strong dipole, like a ferroelectric, then the electrons at the bottom have a different energy than the electrons at the top, like a capacitor, you see? Like if I put a capacitor, then all the electrons' energies are shifted, you see? And I feel like the potential drop is so high in ferroelectric that this should be possible with like 1 or 2 monolayers of material. So anyway,
Okay.
maybe it's wrong. I can we can talk to Eric too because he knows a lot about this. Maybe
Okay.
it's crazy, but I think it could work. Okay.
Okay. Thank you.
Okay, so thanks again. And now it's my pleasure to introduce the last speaker of the day, Ariana Sherban, coming from EPFL Switzerland. It's yours.
So, firstly, I would like to thank everyone for inviting me here. I'm quite nervous because I used to work here some couple of years ago. So I see so many faces and I'm very thankful that I'm home. I cut actually the title because the view is much nicer. So today I will present self-supported catalyst for hydrogen evolution reaction. Oops, I'm trembling. So the motivation actually, as you see, the global direct primary energy consumption has increased dramatically, but still the main sources of this energy come from coal, oil, and gas. This is also related to the significantly high amount of CO2 production. So annually we are producing 40% gigatons of CO2. So in 2022, we are at the peak of our society, but from solar and wind energy surged to make a record of 12% of the world's electricity, but it's not enough. So actually it's an energy mix problem with a significant CO2 footprint. So someone actually thought that water will be one day employed as a fuel, and actually it's right now. So to talk about hydrogen production, we are talking about different colors, how hydrogen is produced, but I think we should be focused more on green hydrogen without any CO2 release, just for a sustainable society. So as talking, why do we need actually hydrogen? We need for ammonia production. 55% of it, it's going there. And we all know how important ammonia it is. So if we are talking about energy coming from water, we are talking about water electrolysis. And here we have two technologies going on in two mediums, alkaline and also acidic. So firstly, it's a membrane-free one, but it's low performant. It's a mature technology. It has a lot of losses, and also it is quite expensive. Going for more steady technology, we have in acidic medium, we have the PM water electrolyzer. So it's a polymeric electron membrane. So we have actually the protons going from the anode to the cathode. Here the technology is much more performant, but also there is the platinum group catalysts are used, so it's quite expensive. To combine both technologies, also the advantages of all of them, there is a new one. The technology is still in development. So as mentioned, we have the anionic exchange membrane water electrolyzer, which allows us to have high performance, but also PGM-free catalyst. So as I mentioned, we need performant catalyst and also performant membranes, as mentioned. So if we are talking about an electrolyzer, the input is electrical energy, and then the output is chemical energy. And we have an anode, where the oxygen evolution reaction occurs, and also the cathode, where the hydrogen evolution reaction occurs. So in this case, in alkaline medium, the bottleneck reaction is the hydrogen evolution reaction. In the other side, in the acidic media, actually the oxygen evolution reaction is the bottleneck. So therefore, we will go directly to the cathode side. And here is the Sabatier principle, and we all know if it's a weak binding energy, actually the reactants, they don't have time to react to bind with the catalyst. Then if we have strong binding energy, then we hinder the desorption. And then we have the optimal binding energy, and then we have platinum. This is the state of the art. But of course, a lot of trials were made for for PGM-free catalyst, and you can see here we have quite a lot of options. But there are very good electrocatalysts, as mentioned, but with very low overpotentials in a very low current range. So if we want to implement, so to jump in the gap of water electrolyzer, we have to put more focus on overpotential at high current densities. So as I mentioned, the goal is to have AGR high performance at large current densities. And of course, we have requirements. So we have to enhance charge and mass transfer. We have to have high intrinsic activity. We have to accelerate bubble detachment. And also we have to improve stability at all. And for this, we have also some solutions. So we have morphology engineering, chemical engineering, combining active moieties with carbon. And this is a very nice paper in ACS Nano. And for now on, I will go with the self-supported electrocatalyst. So morphology engineering, actually, this is the solution I chose. So at the moment, as I said, we have the platinum on carbon is the state-of-the-art catalyst. And the aim of this work was to develop nickel-based catalyst supported on different substrates. Of course, to use available substrates to assess the AGR activity in a 3-electrode setup, and I will explain later, but also to integrate this catalyst into a membrane electrode assembly, so in the device itself. So here we have just one-step electrode deposition technique. Here we have some substrates as nickel mesh, nickel foam, nickel paper, stainless steel paper, carbon paper. After the electrode deposition, all the substrates are covered by our catalyst. So here it's an LSV. For those that they don't have a contact with electrochemistry, we want this voltage to be very close to zero. So we have that we see that we have a very high overpotential for nickel mesh. If we are tuning the properties of the electrode deposition, we can obtain actually at 1 amp a catalyst that shows around 270 millivolts. So it is quite good. And as to a short reminder, the electrochemical's active surface area allows us drawing a connection between the active catalytic sites and its activity. And there is like the formula. So here, by calculating the double layer capacitance, we can see that the nickel-based catalyst on nickel mesh has the highest one. So as a reminder, the aim of this work was to develop AGR robust catalyst for high current densities. A new method for this was developed. One method that is very versatile, it's one-step synthesis, it's scalable, it's reproducible, it's cheap. We assess the AGR activity in a 3-electrode setup configuration, a normal lab one. We use available substrates, and let's go to the integration of the catalyst into the membrane electrode assembly. So here it's a water electrolyzer, an anionic exchange one. And here it's more complex because we have two reactions happening at the same time. We have also a polymer. We have how we are doing our membrane assembling. Also, we have a lot of interfaces. Interfaces are very challenging. Also, we have a lot of contributions coming to activation, ohmic, concentration, and so on. But I would say stability is very important. So here it's a normal membrane, anionic exchange membrane. It's available. It's a benchmark in this field. It's called Sustanian. And here we have a PGM-free anode and cathode. And it's operated at 1 molar KOH and with 1 amp per square centimeter. As you can see, the voltage is around 1.9. So the state of the art, it's PGM catalyst, Sustanian membrane, and the cell voltage is around 165. So here we have the cathode anode PGM-free catalyst. Also we have an anionic exchange membrane, it is homemade. So here we can see that actually at 1 amp per square centimeter, we have 1.5 volts. So it's quite close to the state of the art. Also 100 hours, the degradation is quite low. We have longer stability tests as well. So conclusions and future perspectives. So we developed robust AGR catalyst for high current densities. This can be implemented directly in the system. The optimization of the deposition was done. Also the benchmark for the electrochemical performance. Also surface and bulk characterization techniques, they link to the performance. and for future perspectives of some operando XRD and SAS measurements to see actually the mechanism behind this catalyst. So to acknowledge, I would like to acknowledge Chile, and then my colleagues, also Iwi. Okay, she's there. She's there. And she actually will have a very nice work on this water electrolyzer, also in DI water, and also in 1 molar KOH with a lot of stabilities and very nice results. Also Nanjin is the tall one. He's doing the membranes, very nice. Also the other ones for helping me with TM, with also with XPS measurements. And in the last part, I would like to thank the team from Taiwan and also to the beamline scientists from Japan. So thank you very much. Oof. I was planning to come with a lot of results, but I cannot because it's under a patent and my professor didn't allow me to show you more. But I was very excited about it.
Still you showed Iwi, so that's good. So, nice to see her again. You mentioned that you use 1 molar KOH.
Yeah.
So my question is it also on the cathode? You use both anode and cathode?
Yeah.
I see. So do you have any data with no KOH in the cathode?
Yes.
No water in the cathode?
Yes.
And you mentioned something about the results?
Yes, we will have a very nice paper about it with the dry cathode and everything, with stability more than 1,000 actually hours, with performance at 5 amps or more. So you will see.
Okay, looking forward. Thank you. Nice work.
Okay, other questions? No? Okay. So, I want to congratulate you for your work, and we will wait for the paper to be published, and then the questions. Okay, once again.
Want to make an announcement. So we will have a very short coffee break, so 10-15 minutes, because we will do a visit into our institute that is 5 minutes away from here. So let's say at 4 and 5 minutes to be outside. We will walk until the institute. Please take all your belongings. And from there, the bus at 5 o'clock, 5:15, will take us and we will go to the restaurant. The one, to the touristy guide. Yeah. So please be in time. Thank you to all the speakers of today.